Вот. Вот этот?
Okay.
Вот это. Лево,
Sure, okay. So, sorry, now it's clear. So, all other events happened 30 years ago. At this time, during 30 years, the laser technology took a very good position in many fields, especially in microelectronics. For example, when you look for mobile phones, it's impossible to find even one item which made without laser technologies. But absolutely different. Again. Да нет.
Нажимаете лево-право.
But absolutely different situation with transparent materials, and in laser radiation cannot be used for treatment of transparent materials. That's why in late 90s appeared some methods, or so-called some Japanese persons, Koji Sujoka, invent methods so-called LIPA, laser-induced plasma-assisted ablation. The scheme of LIPA is now here. You see the laser beam, you see the transparent material, and through this material, laser radiation goes to the target, in this case metal target, in the plasma and vapor produces is etched or ablate the transparent materials. Just after this work, Hiroki Niina made the LIPA method, laser-induced backside wet etching, and after that appears LIPD, dry etching, live front etching, BBH, black body heating, and many others. So all these methods use the laser-induced plasma. But in spite of it was done many works related to using of laser-induced plasma, till now the real methods for microstructure, for treatment of transparent materials does not exist. All the lasers which was used in those different methods was absolutely different, and occasionally. Sometimes it was excimer lasers, sometimes solid-state lasers, fiber lasers, different lasers. All targets was absolutely occasionally. In some cases metals, in other cases even liquids, in some cases thin films. So nobody knows what really case is necessary to produce the good, adoptable, enough precise and comfortable in control and productive methods of laser-induced plasma treatment. Even more, the working agent is a plasma, but nobody even try. Maybe I know less than figures in my hand, works which was devoted to study the properties of the plasma. It's really not so easy. It's not freely expanded plasma. It's plasma in between target and the sample, very small in confinement mode. But anyway, it's necessary to study it. That's why we decided to do it. And in this case, I will say about the idea, about the principal schema, and about the experimental in this part. In this slide, you see the transparent material, you see the target, black body heater, you see the plasma area and the laser beam. And what a question we should to decide before we develop this method. This is 3, maybe 4 different questions. First of all, it's which laser is necessary. It's a very important question, and one time I made a talk at the alt about this idea, but a few years ago. But most important, what we really understood at this time, that the best laser is the same laser which is used for microstructuring of highly absorbing materials. The only task in this case is to transform not absorbing material, glass, in highly absorbing by conversion of laser energy to energy of plasma. I don't know, so idea is the laser is already optimized for microstructuring of surface. I mean the pulse regime, the pulse duration, pulse repetition rate, the spot size, even the energy. Only we should take into attention the conversion coefficient from the laser energy to laser plasma. We should consider some losses, the heating losses, the ionization losses, the radiation losses. Fortunately, all of them is small enough relatively to the energy which goes to ablation of highly absorbing material. So the next question, what should be the target? From one point it's easy, it should be good absorption, small reflection, sometimes in contradictions. It's also the properties of plasma important. The temperature and the lifetime of the most important component of plasma. Also special temporal characteristics is clear more or less from the above mentioned. It should be pulse plasma and confinement mode to keep the pressure and to decrease the heat losses. Also we should pay attention for mechanism of removing of material. And working scheme in our case is presented at this slide. This transport material at the left. Oh, 5 minutes. Okay. Okay, this is a scheme, and я же не в 10 начал. Надо минут. Okay, and we took attention for the properties of plasma and the bispectral and bi-ultrasonic and the temperature of most intensive components C2 radicals is 14,000 kelvins, and the amplitude of the pressure of the first maximum is 1 gigapascal, but I have no time to go in details. And the mechanism now it was some argues on this point, but now is clear because the ionization degree is small, so we can, and the mechanism mostly has a thermal character, and more of this because intensity of silicon is also small. It means that partially this silicon evaporates under the heating by C2 radicals, and partially is avoided, is removed by the pressure of vapor. And the geometrical characteristic is diameter of this plasma is equal to the diameter of laser spot, and the linear dependence in this region from the number of pulses and from energy. So above of this perfect controllability. And so finally we have the fiber laser, which is the best for microstructuring of surface of absorbing material, also is the best with the target from graphite for transparent materials. And now I go to part 2, to applications of LIMP. Our approach is we first calculated what should be the sizes and deepness of treated zone. We fabricate it and we test it. And in this manner, we made many of optical phase components, but about these components I had in my first talk in the late. Now I like to say more, a little bit more, about transformation of Gauss beam to Bessel beam. You know this is important task, and the best instrument for do this transformation is spiral phase plate. Spiral phase plate is quite complicated device because it needs to produce many sectors, then more than better. The 20 is good enough. With spirally changes the thickness, and with this such components we can change not only the distribution but polarization of the laser beam, of the optical beams. And we did it, and this is a result, and this is the result of testing. You see this color faceplate at the left, which produces the Bessel distribution from Gauss, the annular distribution, and you see the vector retarder, varying retarder, which produces from linearly polarized light the azimutally or radially polarized beam. And the right side, this is a test with a fiber laser and with drilling of thin films with radially polarized in the up beam, in the middle with beam azimutally polarized, and the down in the linearly polarized beam. You see the big difference in that. And now I go to the future. I need 1 minute more, and I have 2 more slides. So it's a first example. When I say transparent materials, it could be transparent materials for different wavelengths. For example, silicon is transparent for 10 micrometers, 10.6. But glass is highly absorbed in this region. So we can treat, and we did it, and we received the diffraction grating on silicon using the target as a silicon dioxide. And the next idea is to use chemically active plasma, for example, fluoroplast with carbon, okay? And in this case, carbon, this reaction have place in productivity increase in high degree. And this is last slide. Last slide was similarity between this plasma and microball lighting. And this is all right. So I finished my talk, and thank you for that.
Is it important the target area of carbon, or is more important is more important volume of plasma, or is temperature? So the question is about if we have a carbon nanodrags, so the small carbon area, could we expect the nano and milling or nano drilling?
I understand. You are interested is it possible to go in the small size? Generally, it is possible, but how will you concentrate in the small part, in the small disk, through the glass? This is a question. We can go now. We have 30 micrometers. I think it's relatively easy to have more, maybe 10, maybe a little bit less, but to go deeper in the small size, necessary to think. For example, I think it's possible with some extra ideas. For example, maybe you know about peaking, for example, it was published, peaking of thermochemical effect, because the distribution of temperature inside laser spot is different. And the thermochemical and thermophysical reaction speed is highly dependent on the temperature. That's why I think we have made first experiments, but not enough, for thermophysical peaking. So the size of in the middle of the laser beam, of the laser spot, is much higher than at the periphery. In this case, I think we can go in the smaller size.
Thank you very much.
Yeah. After.
So we will proceed with next, because presentation is given by Gabova. Other plasma source, powerful unipolar terahertz generation.
Yes, okay, this is working. Okay, so good morning, ladies and gentlemen. My name is Diana Gorlova. I'm from the Laboratory of Relativistic Laser Plasma, Lomonosov, Moscow State University. And today, I would like, on behalf of my laboratory, present our recent results concerning the generation of terahertz radiation and the interaction of relativistic laser pulse with terawatt and petawatt, obviously on the in simulation peak power with dense plasma. So what we study generally is the laser plasma acceleration. A generic laser plasma accelerator can be seen as follows. You have vacuum, obviously, because you do not want to disturb your laser pulse. And you have a laser pulse of relativistic intensity. Relativistic meaning that the oscillatory velocity of electron in the field of such laser pulse will be close to the speed of light. So in the case of titanium sapphire laser, it would be 10 to the 18 watt per centimeter square intensity. So we have that. Obviously, the ionization of matter occurs at much lower intensities, and the interaction of the main pulse with the matter will occur with the matter as a plasma. So obviously, the ionization, like several electrons will be cut off from the ions. And then this plasma will be a source of different particles or radiation. And usually what people study as the applications of laser plasma accelerators is, first of all, using this plasma as a source of accelerated electrons or ions, as a source of high-power X-rays, nuclear photonic studies, laboratory astrophysics, and recently, and it is quite a recent development, I think it's 4 or 5 years, that our community began to study this, is the generation of high-energy sources of terahertz radiation with high energy and also high spectral power density. And this is what we began to study. So briefly, what is terahertz radiation? I think most people know about it. The terahertz radiation is the radiation with wavelengths between 1 millimeter and 100 micrometers. It didn't have a lot of very efficient sources, but right now there is a lot of sources of terahertz radiation, both narrowband, such as different type of lasers, terahertz FELs, and also backward wave oscillators can also go to terahertz range. But also a lot of broadband sources, such as antennas, optical rectification, conventional accelerators are also used to generate terahertz radiation with high efficiency, filamentation, and as I told quite recently, relativistic laser plasma. So why do we even study it? Why do we study terahertz radiation from such an unconventional interaction? It has some interesting features that cannot be replicated on other sources. First of all, we have a built-in synchronization with the source of electrons, ions, and X-rays, which has a lot of quite unique possibilities for pump-probe interaction. Also, no energy saturation, because we interact with plasma. There is no matter to be broken here. The plasma is already broken, and in perspective, we can generate terahertz radiation with like joule energy levels and higher. And also, we have quite high field strengths. In simulation, people propose the field strengths up to terawatt in terahertz range, which obviously opens the possibility of study relativistic optics and highly nonlinear effects within the terahertz range. But right now, what parameters of terahertz radiation can be achieved? So energy, experimentally up to millijoules and even hundreds of millijoules. Peak field, experimentally achieved is at up to gigavolts per meter, but theoretically predicted up to like terawatts and much higher. The usual conversion efficiency that is reported in articles for laser plasma accelerators is up to 1%. Usually it's like fraction of the percent, but 1% would be what we strive for. And obviously the terahertz radiation that we produce can have a lot of applications. Security screening is more general, but what this high power terahertz radiation can be used is obviously the fundamental study of carrier dynamics and also like chemistry and catalysis and so on. And also, as we also do study acceleration of electrons, we use this terahertz radiation as a diagnostic tool, obviously, because it's generated by electrons and currents, and some properties of these electrons are imprinted in terahertz radiation. As for laser plasma accelerators, there are several mechanisms that are reported in the literature that allow us to generate terahertz radiation. First of all is linear conversion. So basically, if you have a plasma wave that has a wavelength in the terahertz range, under some conditions, and it is quite an interesting topic, it can convert, it can emit the radiation in the terahertz range. The second, and I think it's right now the most studied, would be the coherent transition radiation. So the radiation that occurs when the charged particle crosses the boundary with two media that have different dielectric properties. Also, we have so-called sheath radiation. This is the radiation of an accelerating dipole consisted of accelerating electrons and ions, but it is quite a specific mechanism. And also, as in filamentation, we also have different and high density currents that occur within laser plasma interaction that exist at femtosecond to picosecond time scale and also emit within the terahertz range. So this is the main mechanism. And in a setup in Lomonosov Moscow State University, we did study the generation of terahertz radiation within our interaction. So what do we study? We have a two-pulse interaction setup. First of all, as a target, we used a 16 micrometer plastic tape. So it is solid state target. It has quite a high density of electrons. So it would be overcritical for titanium sapphire to interact with acids. To lower the density of electrons, we use a so-called pre-pulse. So we use a nanosecond laser with intensity up to 10 to the 12 watt per centimeter squared. It pre-ionizes our tape. It creates a layer of under critical density plasma, so the density would be like tenths of % of critical, and the length of this layer would be several hundred micrometers. And with this layer, so a target is basically the layer of under critical plasma, a main pulse with intensity of 5 to 10 to the 8 watt per square centimeter will be interacting. And within this interaction, we studied the properties of accelerated electrons. We used some scintillators, spectrometers, and so on. And we studied the properties of terahertz radiation. And as a detector, we use Golgi cells, and we also just studied this as is and collected the radiation with off-axis parabola and to study its spectral and angular properties out of the vacuum camera. I also would like to note that because the Golgi cell can only operate in air and all of our interaction happens in vacuum, we need to use a lot of different windows for a vacuum chamber that reduce spectral intensity of the radiation quite highly. So as you can see, it is mostly due to a Teflon window that we use. We are limited up to 5 terahertz. So what we did study, as I told you earlier, is basically a coincidence between the interaction of high energy generation of high energy electrons and generation of terahertz radiation. And as for high energy electrons, we in our setup can generate quite a nice electron beam. It would be collimated. It's obviously not monochromatic. It has energies of exponential energy spectrum in several MeVs. But it also collimated, so the angular divergence would be 0.1 radian, and it is also quite stable. So we have this electron beam, and the charge of electrons, as you can see in this graphic, would be in violet, and in green you can see the intensity of terahertz radiation. So it's not quite coincident, but they're close. But this is only for high energy electrons, so electrons with energy higher than 3 MeVs. If we lower our cutoff energy, as you can see for 1 MeV and specifically for 0.1 MeV, so we detect almost all of our electrons, the coincidence between the generation and acceleration of electrons and generation of terahertz radiation is observed quite clearly. So we established that. And then we measured the angular properties of terahertz radiation. So dependent on the initial density of the target that we interacted with, we have different properties of electrons. So we have generation of collimated beam with lower density plasma, and if we go to higher density plasma, we generate a diffuse beam, but it has 2 or 3 times more charge. So possibly it could be more effective for generation of terahertz radiation. So we studied the angular distribution, and as you can see, for generation of collimated beam, the terahertz radiation generates in a cone. So it's with half angle of about 20 degrees. And if we go to the generation of diffuse beam, the terahertz radiation is generated quite uniformly within the angles that we studied. The spectral terahertz radiation was measured using the Michelson interferometer, and it lies within like several terahertz range. But as I told you earlier, we have quite a sharp cutoff. Also, we studied the dependence from the energy of the main laser pulse, because if you increase the main laser pulse energy, you generate more electrons, you possibly generate more terahertz. And the scaling between the square of the charge of our electron beam and the energy of the terahertz was proportional. So, and also we measured the energy of terahertz radiation, and it was up to 100 millijoules. So conversion energy from our main laser pulse to terahertz is about 0.2%. So similar to those published previously in the literature. And also I would like to note that this is without any optimization. This is just as is, and obviously we can do better. So what do we measure experimentally? Cone-shaped emission of terahertz radiation roughly scales as a square of number of electrons, so square of charge, and also we did measure polarization, and it is highly linearly polarized. And the generation mechanism that explains all of these observed properties would be coherent transition radiation. But for the coherent transition radiation, it's usually need to meet 2 criteria. First of all, we need to have a sharp boundary. And it is unusual to think about because we have a huge, like several hundred of micrometers pre-plasma cloud. So people do not usually think of it as a sharp boundary. But we have this pre-plasma cloud that is of density highly overcritical for terahertz radiation. And the transition between overcritical to undercritical for terahertz is about 10 micrometers, so much, much lower than the wavelengths of radiation. And the second thing that we need to prove would be coherency. So if the length of our electron beam would be smaller than the wavelengths of radiation, the electrons will emit coherently, so the energy density would be scaled as obviously a square of number of electrons. And we also meet this criteria at least up to 5 or 6 terahertz. So the coherent transition radiation, both of these things, both of those criteria are met. And we did study, the theory of coherent transition radiation is quite robust. It was, I think, first published in 1946 by Ginsburg and Frank. It obviously had some updates since then, and we did use this formula to calculate the frequency angular spectra of coherent transition radiation. I would like to note that, first of all, we use a modified formula to calculate the field amplitude of single electron, because in classical theory, the electron crosses the boundary perpendicular to the boundary. We have the angle to modify it because we have a highly, not a highly, but a somewhat divergent electron beam. And also we took into account the diffraction effects, which are of utmost importance, as we have a limited size of boundary, limited by, obviously, the nanosecond expansion of plasma. So the diffraction effects, I think, for all laser plasma accelerators are essential to consider when studying the coherent transition radiation. And here, on the lower four images, you can see the calculated, from the formula I showed you earlier, properties of coherent transition radiation. These are calculated by using the experimentally measured properties of electron beam. And as you can see, it coincides really nicely. So we also have this cone with angle about, half angle about 20 degrees, and the spectrum also lies within like several terahertz range. So we confirmed the mechanism of a generation. And also the shape of a field, so E from T. We didn't measure it experimentally yet, we're working on it, but we did it, obviously it can be calculated from theory, and we calculated the field and also the autocorrelation function, how it would look. And as you can see, the calculated and the measured autocorrelation function correlates really nicely. So I think when we measure the field of a terahertz radiation, I think we will have no surprises here. Also, within the laser plasma accelerators, the main way to study this interaction numerically would be to have a particle and cell simulation. I would not go into much detail here, but we did this simulation. We did it in full 3D regime, and we also achieved quite a remarkable a coincidence between what we observe in experiment and what we observe in simulation. So we basically reproduced our experiment in simulation. We have the electron beam with quite similar properties. And why did we do that? Because to study the terahertz radiation in peak particle and cell simulation is quite hard. To go from the near field to far field for terahertz radiation, we would have to have the simulation domain in millimeters. And for particle and cell simulation, what we usually study is several tens of micrometers. So it would be impossible to calculate. We need to have another approaches to study it numerically. And what we did propose is to use the obtained from particle and cell simulation energy angle electron distribution, because this formula, this double sum that I showed you earlier, it depends on only several parameters. So electron energy and electron angle, we can get it from particle and cell. And also distance between source and the boundary interface, transverse size of your plasma, and electron beam temporal shape. So the properties of pre-plasma can be calculated, the properties of electrons can be calculated. So in principle, using this approach, we can study the terahertz radiation numerically, even if we don't have the laser yet. And first of all, we did the study for the laser that we do have. And here you see the angular and spectral properties. They also coincide quite nicely with what we observed in the experiment. And having that, we did also some calculation for the proposed laser of Excel's laser system. It will be a much more high energy laser system, so the energy in one laser would be 400 joules. For us, it's 50 millijoules, so it's like 3 orders of magnitude higher. And we did study it numerically, the interaction between this laser and thick metal foil. And here you can see the animation of interaction. In green, there would be a high energy electrons that, when crossing the boundary, would generate coherent transition radiation. And we also obtained some energy angular distributions. As you can see, the radiation also lies between like several terahertz, but it also goes up to 30 terahertz, and it also highly collimated in this range. And an interesting thing that we observed is that the field strength for this laser interaction would be up to relativistic in terahertz range. So we were not the only one to observe that, but it also gives us hope that we can generate and study this radiation. So here are conclusions. I think I would not read them. Thank you for your attention. And if you have any questions, I would be happy to answer them.
Thank you very much for your what do we have enough time for many
Maybe I missed, what is the efficiency, energy efficiency of conversion into terahertz?
From a main laser to
Yes.
terahertz, 0.2% for us right now.
0.2.
0.2.
And how did you measure it?
We measured it. Obviously, the Galilei cell cannot measure high energies, so we measured it with focusing and some filters to lower the energy of radiation, and we also measured it in several like angular point, and we also, as we know, the angular distribution and spectral distribution, we calculated the energy, and it was led to similar results.
So maybe the next question. So I think it is beautiful presentation. So it is some, they call it some range between technological applications and technology. So there are some people. Terawatt, square centimeter regime and ultra high. So something between, because usually people say us about the proton acceleration, proton radiography as application, but now it is terahertz and our.
Not only terahertz, also electron beam.
Of course, usually people say about relativistic electron beam and the ion which follow them, and we usually want to accelerate it to some level 10 mega electron volt per atom in proton or even carbon ions. And now we listen about absolutely different applications. So thank you very much. If you don't have some additional questions, so we will close our session and we'll go to drink coffee. Coffee break. Спасибо очень.
Прошу внимания, сейчас будет представлен доклад Ирины Николаевны Завестовской. У нас небольшие проблемы с подключением, но они вот-вот будут решены. Я прошу не расходиться.
У меня, коллеги, у меня стоит второй слайд. Не начало.
So, Professor Inagamov, please give the floor to Irina Nikolaevna Zavestovskaya. So we fixed.
Dear colleagues, I'm sorry for my distant participation, especially in Samara, because maybe many of my colleagues know that I worked in Samara branch of Lebedev Institute during 8 years, and I'm so sorry. And first I would like to express my big gratitude to the program committee and especially to Professor Konov for kind invitation to give our result, our new result in the field of the laser inactivation of some type of viruses, including the SARS-CoV-2 virus. And it's interesting for me, I didn't see the presentation. Did you listen me? Okay. I didn't see the presentation. Фото, я не вижу презентации. Да. Okay. So you can see the second slide, and it's very simple to very understanding the motivation of our work, because the COVID pandemic caused by SARS-CoV-2 coronavirus lasted for more than 3 years. Up to World Health Organization, it was started in March of 20 and on May of this year. And unfortunately, more than 20 million people dead, my father also. And it had to stimulation of search for effective method, not only inactivation, just eradication of pathogenic agents. And I'd like to say what we know about this type of virus and the type of inactivation of them. SARS-CoV-2 is very contagious. It already has numeric mutations. All about this. This have two type of pathogens, and it means that we need to work with this type of viruses in special room, red room, and patients also stay in the same time of rooms. And it is RNA virus and belong to the beta coronavirus genus. And the genome of SARS-CoV-2 consists almost about 30,000 base pairs, and is related to two other pandemic coronaviruses, MERS-CoV by 50% and SARS-CoV by 79%. So here you can see the coronavirus theme, so very, very often mentioned spike protein and RNA genome and so on. Next slide, please. Okay, next slide, please. Okay, and SARS-CoV-2 virus transmission occurs by airborne droplets through water and surface. Here you can see, and it's very important then, this virus can remain viable and infectious for up to several hours in aerosols, up to several days on the surfaces. Here you can see the scheme of some type of surface and how long this virus live on them. And very interesting that incubation temperature is critical, as viruses can remain viable at 4 degrees up to 28 days. But at 30 Celsius, viral viability is reduced. Next slide, please. So, and of course, there is an actual task of inactivating the virus on surfaces by methods that are safe for humans. We would like to use this method just in the rooms with patients, in the flight body, in elevators, and so on. Because the elevators is the most danger places for coronavirus propagation. One of the non-contact and very friendly method of pathogens destruction is the ultraviolet radiation. And like another virus, SARS-CoV-2 is highly sensitive to UVC radiation with wavelengths smaller than 200 nanometers, since it is directly absorbed by nucleic acids, RNA and DNA, and amino acids. However, UVC radiation causes harm not only for pathogens, but for human health as well. This is the reason why the UVC inactivation process must take place in a deserted room that is difficult to achieve in the with a large number of the patient. There is a great interest in the development and technologies for inactivating viruses and bacteria using UV radiation in the safe for human range, so-called UVA wavelengths from 320 to 420 nanometers. Though nucleic and amino acids do not absorb UVA wavelengths, it's possible to inactivate SARS-CoV-2 viruses with these low-energy UV photons if sufficiently higher doses can be delivered. And SARS-CoV-2 viruses, I mentioned this is very pathogenic viruses. Please, next slide. So, in our work is devoted to experimental study of the mechanisms of beta coronavirus inactivation with using the laser diode radiation, UVA spatial range. And the goal was to optimize the radiation power density and lethal doses required for virus photo inactivation, depending on the initial virus titer and the radiation divergence. So the UVA sources with a small step along the radiation wavelengths were constructed in the Lebedev Institute. And for research, two types of beta coronavirus was investigated, SARS-CoV-2 and bovine coronavirus. Bovine coronavirus is considered as a model virus for SARS-CoV-2, but it has a low degree of pathogenicity, and we can use a lot of experiment and then analyze and choose a more optimal wavelengths and do experiment in the red zone with SARS-CoV-2. So, cultivation of the viral models and radiation experiment and studies of the changes on RNA in irradiated samples of SARS-CoV-2 virus were carried out in the Reference Center for Coronavirus Infection in Gamaleya Institute, and spectroscopy measured the changes in the irradiated SARS-CoV-2 virus proteins were performed in Institute of Bioorganic Chemistry of Russian Academy of Science. Next slide, please. So, You can see the stand for virus irradiation. Commercial light emitted diode radiation source were used, and you have the size small, about 3 millimeter, and in order to prevent the heat dissipation, laser diode chips were soldered into the star type board for further installation of the radiator. And here you can see all 8 wavelengths which we use for irradiation, one from UVC range, one from the UVB, and 6 wavelengths in UVA regions. Please, next slide. So, and culture fluid containing bovine coronaviruses was grown in culture SOMDBK, this is the bovine kidney cells, which were cultured in complete DMM growth as a special medium. And culture fluid containing SARS-CoV-2 was grown as a cell culture Viro E6, monkey kidney cells. And then cells were separated from the virus containing liquid by centrifugation, and the virus titer for bovine virus was 10 to the 5, and for SARS-CoV-2 from 10 to the 4 to 10 to the 7. And it's interesting that the Delta strain of SARS-CoV-2 virus was used in the experiments. Here you can see for 24-hour monolayer of cells for bovine viruses. Please, next slide. So, and the culture fluid was irradiated appropriate wavelengths according to the some special study protocol. And here you can see the full scale and the schematic diagrams and the, of coronavirus irradiation in a plate. At the first stage, experiments were carried out with the bovine coronavirus and 8 wavelengths, and the second stage, SARS-CoV-2 for the inactivation protocols were developed, but experiments were carried out in the red zone with only the 5 wavelengths. And virus suspension with a volume of 200 microliter was placed in 4 adjacent cells of 96 well plate and 50 microliter in each cells. And the lead plate system was centered so that the emitting aperture of the laser diode was located strictly above the center between the 4 wells, with virus suspension providing the same distribution of laser radiation for each of the cells. And the aperture of the laser diode was located about 4 centimeters from the surface of the solution. Please, next slide. Next slide. Okay. And how we can estimate the virus inactivation? The system for evaluation and antiviral action of UV radiation consists the quantitative expression of the suspicion of the virus reproduction determined on the cell line as a criterion for antiviral UV radiation efficiency. The difference in the virus titers in the control without radiation and irradiated groups is presented, expressed in logarithm. In virological studies, the action of the drug is considered to be a satisfactory antiviral effect when the logarithm of the titer more than 2. So, In fact, the sensitivity of the virus to UV radiation was defined as the effect of the reduction of the titer in the virus to order of magnitude or more. Please, next slide. Next slide, please. So, and here you can see the result. I'd like to say that it was effective irradiation of beta coronavirus bovine as well as SARS-CoV-2 by UV radiation for all wavelengths and dose-dependent decreases in the infection titer we have. And threshold value of the radiation dose, and here you can see just in this left you have an activation of bovine coronaviruses by radiation with the different wavelengths. You can see all 8 wavelengths. And we have the total inactivation for the wavelengths of 371. And for SARS-CoV-2 virus, you can see the dependence also, the titer on the doses for 6 wavelengths. And for the bovine virus, we have the critical fluid of laser radiation from 0.0 per centimeter square at 270 nanometer to 7.8 joule per centimeter square at 5 nanometer. And the best result for coronavirus we have with the 371. So, next slide, please. I forgot that I can't. The bottom. So, and we would like to see how our laser divergent radiation and the value of the fluids, how our result depend on this value. And we can say that there is no significant difference in the magnitude of the decrease in of virus accumulation and different roles of the virus containing liquid. But it's very interesting that we have a big dependence on laser diversion. If we use 10 or 9 cells or 4 cells, we have a different result, because for 4 cells, it is obvious that the power density distribution over the surface of the sample is more uniform. And if you have more cells, the radiation power density is noticeably reduced, and the required dose of virus inactivation achieved within the set of radiation time. Next slide, please. So it's very interesting to try to understand what is the mechanism of this inactivation, because no direct absorption there in this material, in these viruses. And to determine the mechanism for the inactivation of coronaviruses, studies of changes on RNA in irradiated samples of SARS-CoV-2 as a result of exposure of UV radiation were carried out. And not only RNA and structural proteins also. And for RNA, this work was in the Gamali Institute and in red zone, and analysis on polymerase chain reaction showed that irradiation leads to degradation on viral RNA and a decrease in the amount on whole RNA by an order to magnitude. by an order of magnitude, which leads to a loss of the ability for the virus replication in the cell, and may be one of the mechanisms of action of radiation. And the fragmentation of RNA genome was investigated exposure of the virus and radiation with a wavelength of 389 nanometer. And here you can see the analysis of CT values obtained using this polymerized chain reaction. And CT volume for 19,000 fragmentation by one cycle and 11,000, more than 11,000 fragmentation during irradiation for 90 minutes. Next slide, please. So, and we have Gamali Institute, we get some coronavirus proteins irradiated and study the changes of protein in irradiated samples of SARS-CoV-2 virus, also as a result of exposure of UV radiation. And so we use two types of proteins, because we know that the penetration of coronavirus into the host cell is mediated by the interaction of cells with a spike protein, which includes as a receptor binding domain. And we investigated the receptor binding domain. This is a short immunogenic fragment from the SARS-CoV-2 spike glycoprotein that binds to a specific endogenous receptor to gain entry into the host cell. RBG consists of 233 amino acids. And other protein we investigated was a nucleocapsid protein. And nucleocapsid protein consists of 419 amino acids, and it is 91 and 48 similar to SARS-CoV and MERS-CoV respectively. And protein samples from SARS-CoV-2 virus irradiated at wavelengths 300 nanometer at concentration, very small concentration of 1 millimeter, diluted in 50 microliter of phosphate buffer saline. And here you can see the three-dimensional structure of RBD of SARS-CoV glycoprotein. Next slide, please. So here you can see the Raman spectroscopy result. And the analysis of changes in position of protein shows that there are changes in the intensity of peaks responsible for specific types of bonds. On the Raman spectra of the nucleocapsid and RBD proteins, there are some peaks presented only on the irradiated sample, and the change may indicate the distribution of protein molecules or the loss of some bonds, which may be due to the chemical transformation. And changing the bonds between molecules in structural proteins can directly reduce the ability of the virus to both penetrate into cells and preserve the integrity of particles, as a result of which they can also lose the infectivity. So next slide, please. So, as a conclusion, I'd like to say that the effective inactivation of beta coronavirus bovine and SARS-CoV-2 by UVA radiation, very friendly for human, for all investigated wavelengths and dose-dependent decrease in the infection titer of the virus was shown. And in accordance with the recommendation of the Pharmacological Committee of the Russian Federation, with a decrease in the infection titer of the virus more than 2 logarithm, the technique can be used as an antiviral agent. And the results can become a ground for development of UVA designification technology, safe for human, which can become promising with using in the room with patient. And it's very interesting that it was found that the threshold value of the radiation dose, which provides a decrease in the virus titer by 2 orders of magnitude, depends on the radiation bandwidth, radiation scheme, and depends on the divergence of the laser diode radiation. And studies on changes in the radiated samples of SARS-CoV-2 virus RNA and structural proteins as a result of exposure UV radiation were carried out to determine of the mechanism of photoinactivation for coronaviruses, and it was shown that degradation of viral RNA and changing the bonds between the molecules and the composition of structural proteins, which leads to a loss of virus infection. Of course, this is just at the beginning result, just the first result. And it is advisable to continue research on the effect of radiation on the structure of protein and maybe RNA. It's very difficult because it's what carried out in the red zone. Conduct a number of functional tests on the ability of RBD and nucleocapsid protein after iteration to participate in intermolecular interaction. And so next, please. Next slide, please. Next slide. So I would like to give a lot of my thanks to all our big team from Lebedev Institute, from Gamma Ali Center, and from Institute of Bioorganic Chemistry. You can see all our participants. And the next slide, please. So thank you for your attention. So. Dear colleagues, I don't know, maybe. So, nobody listen?
Не, все слышали.
Have you any questions?
Irina Nikolaevna, thank you very much for this very broad
So
and comprehensive
if you
presentation.
haven't no questions,
Yeah.
I'd like to say
do you hear
thank
me?
you
No.
and stop my presentation.
Please,
Okay.
please stay with us. Do you hear us, Irina Nikolaevna?
Yes.
Okay.
Yes.
I would like to thank you for this presentation, very broad and comprehensive. I have a question. The mechanism of elimination of viruses in this case is the absorption of RNA. But RNA is also present in the healthy tissue. How to distinguish, how to arrange it in a way that this radiation would not affect the healthy tissue, would not create some mutations, and at the same time would suppress regeneration of viruses. How it's possible to arrange?
Thank you for very good questions. I thought that this is just the first in vitro experiments, and of course a lot of questions we have, and we have result for the degradation RNA just in SARS-CoV-2 virus radiation. This is a part of SARS-CoV-2. So, and no RNA in our all our organism, just for SARS-CoV-2.
So they are spectrally can be
And
distinguished.
this is, you know that we use only UVA radiation. A means that it's very fragile people. So not C radiation. This is the A radiation, about more than 220 nanometers. You can use this radiation many hours, not days, but many hours, and you can have in this reaction the dose enough, because we have the dose-dependent effect.
Thank you. Thank you very much, Irina Nikolaevna.
Not at all. Okay. Thank you. So,
So this session is closed at the moment. We have a coffee break, and we are back in 15 minutes, I think.
dear colleagues,
Irina Nikolaevna, thank you again for your bravery and excellent talk. Thank you.
Vitaly Ivanovich, thank you.
Dear colleagues, my name is Anton Popov and I will chair this session. So we are starting our second session today on laser-matter interaction, and we will have 5 talks according to schedule. I hope that they will be all 5 talks. And we will start our session with a talk presented by Nail Inagamov from Landau Institute for Theoretical Physics of Russian Academy of Science from Moscow, Russia, and the title of his talk is Final Surface and Subsurface Structures Formed as a Result of Laser Action. So, Nail, you have 20 minutes, and 3 minutes before the time limit, I will stand up indicating that you... yes.
Thank you very much for introduction. And чуть ничего не видать. А не видно. А? Вот. Не то. Это следующий, это второй.
So the talk should be given by Nail Inagamov, and the title is Final
Да, вот
Surface.
это.
Okay.
Ага. А листать, вот это, да, второй. Листать, да? Oh, so thank you very much for invitation. And this is our team from different Institute of Russian Academy of Science. So the laser light easily produce high pressures, and we are interested in something multi-megabar pressures. Okay. So we use femtosecond laser pulse and something 10, 100 joule per square centimeter fluences of incident radiance. It's easily pass through air because it is slightly below optical breakdown for air. And if you use wavelength and target which absorb significant part of the incident irradiation, when we easily obtain huge pressures. But it is, of course, estimate. You see, we just divide energy absorbed to the skin depth where energy is absorbed. So few tens, 100 megabar is easily produced, but of course in this very thin layer. And I just want to emphasize that the melting and subsequent crystallization are very important for establishing of crystallographic structure of the crystalline. Because the crystallization rate, in our case, the spatial range is small and crystallization rate is high. Just has some examples. So we have some focal spot on the monocrystal and irradiated, and after that it was molten, and after that crystallized, and you see some very long crystalline crystallite domain crystallite which appears during this crystallization, and it may be observed also experimentally. So outside the focal spot you see one crystallographic structure, while inside it you see very long, radially elongated crystallite. With changing polycrystalline structure, you can create matter with new properties. And there are two ways to melt. So one is conductive melting, and the other one is something like dynamic melting by high pressure and dissipation in the shock wave. So we use the second one. So for example, in the case of titanium, its heat conduction is very low, so you conductively can melt it just a few tens nanometer. But if you create multi-megabar shock and it penetrates deep, the molten layer will be much thicker. And how deep it is. So this is typical diagram taken from this specialist who developed this semi-empirical equational state based on many material parameters. And we plot here. So here it is a melting curve. You see this L. This means liquid. So above this solid line, it is liquid. Below, it is solid. And you see for titanium, you have many polymorphic inside titanium, depending on temperature and pressure, many polymorphic phases. And you see this Eugonio curve, which intersect melting curve somewhere for this equation of state, somewhere between 1.5 and 2 megabar. There are also another, for example, Curly, so Eugonio, melting line, somewhere in 2 megabar region, intersection. And if you, in our case, we not just send a shock, we have a combination of shock and release isentrope. So the pressure, so I plot here 3 circles, blue one, red one, and green one. So blue one is the titanium before shock. So it has room temperature and 0 pressure. After that, it comes somewhere here. It depends on the pressure in the shock wave, which few megabar easily is 100 GPa is 1 megabar. After that, we have release, and if release is higher than the melting temperature of titanium at 0 pressure, we will have, after release, we will have molten titanium. Okay, but in this point, we come into some contradiction between models. So from shock wave data, people plot this one, liquid, solid. But in a laser heated anvil experiment, diamond anvil experiments, they measure much more lower melting curves. So it is somehow like, at this plot, it will be something like a horizontal. At 1 megabar, it will be just 10% higher temperature. So we don't know who is right today, maybe due to melting condition, because in a laser heated anvil experiment, you do it long time. And in shock, it is different conditions. So we don't know who is right, who not, but we just develop our hybrid code. So we divide 2 temperature zone and proceeded with Hydra code, and inside the depth, we use molecular dynamic code. And this is real experiment, so we have fiber laser in these squares, and the forecast laser beam here with different fluence. And from our estimates, in our simulation, something like 5-10 megabar pressure is achieved here. Our simulation gives thickness of the molten layer of order of 1 micron. And after that, we did this micro-analysis of the structure, and we see some, so initially it was monocrystal, and after illumination, we obtained this polycrystalline structure, 1 micron thick. And below it is initial monocrystal, but with large density of dislocations. And we have definite boundary which divide them. And what we see here, I just put a scheme, so we see long crystalline oriented parallel to the surface. It is new. I think nobody ever seen such long crystalline parallel. Usually people see this perpendicular. And we have different orientation, oblique, perpendicular, and at the bottom we have this long, and we have some explanation for this in our paper. And this is, at the left side we see the focal spot. And the central area is the area of the highest fluence. And we take lamella from this central pot. Lamella means that you do ion milling and produce some plate, 8 to 8 micron, and then you see it transversely by transparent electron microscope. And this picture to the right is obtained by this technique. And if we see to this central area from scanning, electron scanning microscope, and this is our lamella size, we see this rippling. It is rather well known. People many times obtain, beginning from the work of Anatoly Vorobyov, such kind. But usually we do it at much lower intensities. So here it is intensity which produces 10 megabar pressure. And in the corona, the plasma has temperatures of order of 100 eV per atom. But even in this case, we produce this structure. Okay, and why I attract your attention to this structure? Что-то не листает дальше. Листаните, а? Следующий слайд. Вот. So we connect the structure with the disorientation of the energy flux. Так, немножко раньше. А, черт. Так, вырезали. Вот смотрим сверху. So it is up a view.
Black screen, we don't see anything.
Вот. And this is typical, I show it many times. So by laser irradiation, you produce some foam, and this foam has some membrane, and the structure which appears at the surface strongly disturbs the fluxes, the heat fluxes. So at the boundary with vacuum or air, you cannot, it is thermally isolated, so you cannot have flux which is normalized to the boundary direction. So you have something, this is red one, arc is of temperature line. So you have some not planar isotemperature lines, not planar, but strongly curved. And therefore the heat fluxes is oriented in different direction. And we connect this inhomogeneity in the heat flux with this structure of this crystalline orientation in the final crystallographic structure. And with this I want to finish, and I want just conclude that we can, with usual femtosecond millijoule, 10 millijoule energy per pulse, titan subsphere, and second harmonic, we can easily produce megabar pressures, and it melts solid up to order of 1-2 megabar. So of course, when penetrating deep inside, it decays, but from 50 megabar to 1 megabar, it passes significant thickness, and all this thickness will be molten. And this unusual quick crystallization made crystallographic structure may be potentially used for some practical application, because it has very different tribological and so on properties. Thank you very much for your attention. Thank you.
Dear Professor Nagamos, thank you very much for your presentation, and we have time for several questions. So please, first.
Oh, thank you.
Okay. My question is, did you took into attention the difference between laminate and turbulence flowing, and could you calculate the threshold between these two regimes?
It is not turbulent. We don't have any Marangoni effect. But it is non-one-dimensional, of course. But still, if you calculate Reynolds number, it will be not 1,000, not 100,000. It will be something like 10, 100, not large. So in your question, answer is it is laminar.
So you calculate only laminate regimes, I think.
Yes.
It means this. Okay.
So we have time for some more questions. Are there any? Okay, I don't see any more questions, so thank you very much for your presentation. So, and this section is actually co-chaired by Ekaterina Barmina, and she will present me the next.
So our next speaker will be Anton Popov, and he will present us results about photothermal application of laser synthesized nanomaterials. Please, you have for all 15 minutes. Please, Anton.
Okay, thank you very much. So, first of all, I want to thank the organizers for inviting me to this great event. And I represent Bio-Nanophotonics Laboratory from Moscow Engineering Physics University. And in our laboratory, I'm responsible for most of the experimental works. And today I want to present you some of our results on synthesis of nanoparticles having a high optical absorption and their application in photothermal domain, let's say. So first I want to say a few words about techniques which we use to make the nanoparticles. And we usually produce the nanomaterials by method of laser ablation in liquid. There should be a video, but okay, doesn't work. Okay, there should be a video demonstrating the process. So the basics is quite simple. So we take a piece of material, put it in some vessel filled with some liquid, typically with water, and then just irradiate it with a pulsed laser radiation, and that's it in a basic case. And for historical reasons, we usually use ultra-short, a femtosecond laser pulses for laser ablation, and this regime is often called fine ablation, and it has several, let's say, advantages over longer, let's say, nanosecond ablation. So what are these advantages? Okay. Again. Doesn't work. Remote control doesn't work anymore. Okay. Come on. Okay, seems like now it works. So what are these advantages? So first, we need much less energy to ablate a unity of material. So basically, we need an order of magnitude less energy than, let's say, in a nanosecond case, so that we can minimize the negative effects related to the generation of plasma and cavitation bubbles. And then we have significant reduction of a heat-affected zone, which again minimizes the ejection of larger fragments. And also there are a number of nonlinear effects, such as generation of white light supercontinuum, which in fact can be very useful to control the size properties of the nanoparticles. And in practice, we very often are using one extension of the laser ablation technique, which is called laser fragmentation in liquid. So in this case, we just remove the target from the cuvette and then focus the laser beam inside the colloidal solution itself and irradiate it. So what can we achieve with this method? So basically two things. The first one is that we can homogenize the size distribution of our nanoparticles and also reduce the mean value. And second, by laser fragmentation, we can produce some complex structures like alloy nanoparticles or core shell structures or core satellite nanoparticles and so on. So our basic research activity is elaboration of laser ablative approach for synthesis of various functional colloidal nanomaterials. And again, for historical reasons, we mostly developed light-absorbing nanomaterials. And as our laboratory is a part of PhysBio Institute, so we mostly applied them for biomedical applications. And light-absorbing nanomaterials can have several, let's say, ways of how to use them in biomedicine, and I want just to mention some of them. So first is the photohyperthermia technique, mostly for treatment cancer, and then it's a closely related photoacoustic bioimaging method where light-absorbing nanoparticles can be used as a contrast agents, and then there are drug delivery, where drugs are conjugated to light-absorbing nanoparticles via heat-sensitive linker so that they can be released under the radiation. And then another major domain is energy, and more specifically area of direct absorption solar collectors. And finally, I want to mention photocatalysis with the reactions like hydrogen generation. So let's go to the examples, and the first example is photohyperthermia application. So the idea here is that if we put the nanoparticles inside the tumor area and then irradiate it with a wavelength at which biological tissues are relatively transparent, then it is possible to selectively destroy tumor cells while leaving healthy tissues unaffected. And so what are the requirements for nanoparticles to be applicable here? So first, they should absorb radiation at wavelengths where biological tissues doesn't. So such spectral ranges are typically called windows of relative tissue transparency, and the first such window is located roughly between 650 and about 900 nanometers. So the second requirement is that this nanomaterial should be biocompatible in the absence of light, and third, they should be small enough to be, let's say, less visible for the immune system. And it turns out that it's not so easy to comply to all these requirements. However, we managed to synthesize a number of materials which can do it. And one of our favorite examples here is titanium nitride nanoparticles, because these nanoparticles, even for simple spherical geometry and a small size, they have the absorption window right in the window of relative tissue transparency. And so we recently, no, not so recently, it's 4 years ago, we managed to solve the bottleneck problem of synthesis of bare water dispersible titanium nitride nanoparticles. So we demonstrated that pulse laser ablation can be used to obtain stable colloidal solutions of these nanoparticles with a variable size from few nanometers to few dozens of nanometers. But what is most important is that these nanoparticles, even for small sizes, so the sizes can be like 20 nanometers, they have a strong absorption in the window of relative tissue transparency, and the photothermal conversion efficiency is among the highest for all nanomaterials. And then we demonstrated this photothermal effect in vitro first. So we used 830 nanometers radiation and demonstrated that this radiation synthesized by nanoparticles can indeed kill the cancer cells even at a very low concentration of nanoparticles. So the concentration can be as low as 10 micrograms per milliliter. And then we take 8 different cell lines and demonstrated that even at 10-fold higher concentration, so concentration like 100 micrograms per milliliter, they don't cause any toxicity. And then we also performed a comprehensive in vivo evaluation. And here we made chemotoxicity tests, biodistribution, and acute toxicity. And here we found that, yes, most nanoparticles accumulate in liver and spleen, but we didn't find any signs of acute inflammation. So all the biochemical markers were within the safe limits. So it means that despite the accumulation in these organs, they don't cause any harm to them. And then we also made a number of light-absorbing materials based on, let's say, classical plasmonic materials, on gold. And you probably all know that gold can very efficiently convert light into heat, but it usually does it in a green range, which is outside of the biological transparency window. And this problem can be solved by making some complex structures based on gold. And so we elaborated laser ablative technique to make a number of such structures, and I'm going to present only a couple of examples. So the first example is so-called quartz satellite nanostructures based on gold and iron. So here we used a two-step procedure. So in the first step, we just synthesized a small gold nanoparticles with sizes smaller than about 10 nanometers. And then we ablated an iron target in the colloidal solution of the gold nanoparticles. And so we got these structures like a core satellite, so a big core decorated by small gold nanoparticles. And we found that they have quite a big absorption in the window of relative tissue transparency, and moreover they have quite good magnetic properties. So this is a multifunctional agent. And another example is again quartz satellite structures based on gold and silicon in this case. So here our synthesis procedure involved a chemical modification step of the nanoparticles by a biocompatible linker, and in this case, so the optical absorption is more pronounced than in the previous case, and moreover, such nanostructures represent a biodegradable object because laser synthesized silicon nanoparticles are biodegradable particles. So this can potentially solve the problem of accumulation of nanomaterials in the organism. Also, these tests are only in the beginning, so we're just starting the tests to verify this this way of elimination of nanomaterials from the organism. Okay. So then, just a very recent result on a new class of laser synthesized nanomaterials. So transition metal dichlorogenides, or shortly TMDC, they have a strong excitonic response, which enables a number of nonlinear optical effects like enhanced generation of second and third harmonics, high refractive index, and giant optical anisotropy. And so, motivated by these benefits, such nanostructures are being rapidly developed, and typically they are produced by methods like electron beam lithography or reactive ion etching. And despite their efficiency, they generally have limitations like relatively low productivity, and they produce nanostructures which are immobilized on a substrate, which limits their applicability. And so to bridge this gap and to expand the applications of these nanostructures, we recently demonstrated that pulsed laser ablation can be used to produce spherical nanoparticles of MOS2 and WS2. And these nanoparticles have a variable size from about 5 to 250 nanometers. And they have a quite interesting internal structure. So look here, while relatively large nanoparticles have a polycrystalline core and shell, which is a fullerene-like or onion-like, so there are concentric spheres. Small nanoparticles, which are smaller than 10 nanometers, they have a single crystal structure. And so these particles also have enhanced photothermal conversion efficiency, generally due to hybridization between Me and excitonic resonances. Then the next application is photoacoustic imaging. I believe that most of you are probably familiar with it. So it generally combines optical methods with ultrasound ones. And here we just eliminate the sample with a pulsed radiation. So sample absorbs this radiation, heats up and produce ultrasound, which we can use to reconstruct the image. And light absorbing nanomaterials can serve as contrast agents here. And the requirements to them are basically the same as we had for photohyperthermia application. So we tried the same type of nanoparticles, and yeah, actually nanoparticles can have additional, let's say, feature in the photoacoustics. They generally have a strong nonlinear response. And so in the first study, we just demonstrated that indeed titanium nitride nanoparticles have this strong nonlinear photoacoustic response. And then we also measured the photoacoustic spectrum and demonstrated that it's somewhat more narrow than the optical absorption one, which is beneficial for the imaging. And then we made photoacoustic microscopy with these nanoparticles and demonstrated that the best contrast can be achieved at the plasmonic wavelengths. And our current interest in this field is application of photoacoustics for measuring concentrations of nanoparticles inside the biological tissues, which is very important for practical implementation of photohyperthermia technique. So here we basically are studying photoacoustic response from mixtures of our light absorbing nanoparticles and the different organic chromophores like hemoglobin, muscle tissue, and fat, and we are trying to unmix the signal from the nanoparticles from the signal from biological chromophores. And our current result here is that for one particular type of nanoparticles, we can detect as low as 0.2% of mass concentration of nanoparticles in a hemoglobin, which is roughly equivalent to 0.25 milligram per milliliter concentration of nanoparticles in the blood. So it's quite a low value which we can detect. So then let's switch to energy application, and more specifically to solar energy. And as you know, solar energy can be used in different ways. So it can be solar to electrical, which is a photovoltaic, or solar to chemical, which is a photosynthesis, or solar to thermal, which is photothermal. So, and one of the most interesting approaches in the photothermal direction is the development of so-called direct absorption solar collectors, or shortly DASC. So in such systems, solar energy is absorbed by a working liquid, and then it is delivered by the working liquid to the consumer. And typical working liquids for the DASC systems are either water, ethylene glycol, or some oils. And while these liquids can very efficiently absorb light in the ultraviolet and infrared ranges, they are only weakly absorbing in the visible range. And so, just as an example, so for a typical DASC system with the thickness of the water layer 10 millimeters, 1 centimeter, so water is the best absorber, but it can absorb only 13%, so 13% of solar radiation in a spectral range from 200 to 1500 nanometers. So this problem can be solved by addition of substances which can efficiently absorb light. But well, what options do we have here? So first option is some molecular agents, some dyes, then nanoparticles and microparticles. However, with molecular agents, with molecular dyes, the problem is that they generally cannot withstand harsh conditions of such systems, so they degrade quite quickly. While micron-sized particles are generally not colloidally stable, so they also cannot be used. So the only real choice is nanoparticles. But what are the requirements for nanoparticles to be applicable for such system? So first, they have high optical absorption and low scattering in the whole solar spectrum. Then they should convert all of the energy which they absorbed from sun to the thermal energy. So there should not be like a photoluminescence or no photochemical reactions. Then they should efficiently deliver this light from the particles to the working liquid. So no or little ligands is preferable. And finally, they should be stable colloidally, chemically, and physically in the conditions of the DASC system. And we just looked at these requirements and realized that laser synthesized materials are quite appealing here, especially taking into account their stability in the absence of ligands. And so we again used our titanium nitride nanoparticles here and found a very impressive results. So again, for typical DASC system with 10 millimeters layer of liquid, so the volume fraction, if we add only 10 to the power of minus 5 volume fraction of titanium nitride nanoparticles, so it can allow us to absorb about 96% of the solar radiation from the whole spectrum, which is a very high value. So, to sum up, I want to say that methods of ultra-short laser ablation can offer unique opportunities for synthesis of a variety of materials having controllable photothermal and other properties, and we already synthesized quite a larger library of nanomaterials having either broadband absorption in the visible and near infrared range, or some narrow absorption bands with a controllable position in the same region. And we also demonstrated their applicability for a number of photothermal applications. And just a final slide. So we have quite a big team, and one of our PhD students, Maxim Savel'ev, will have a poster in the poster session, so please come, and he will explain some details on the mechanism of synthesis of such materials. Thank you for your attention.
Thank you very much, Dr. Popov. We have any question, please?
Please give the microphone, because people online.
Sorry, yes.
You work with different materials for nanoparticles. Did you try upconversion particles? It is a very popular
yes,
type of material. Did you try? Maybe there are special problems in production of them in liquid by ablation. What's
yes,
the
we
situation?
tried, but we actually didn't get quite a good result. It seems like they are losing their properties when they are ablated. So probably we just have a limited experience with it, but with our first experiments were not so successful. And as a first step, we didn't succeed, so probably in future we can elaborate some more on this.
Thank you. So I just want to ask, I don't understand well in your optoacoustics. So you have a particle, nanoparticle, and it oscillate and send acoustic wave inside a liquid, inside colloid, or how?
Yeah, so in photoacoustics, so basically we are mapping the distribution of absorption coefficient, of optical absorption coefficient.
Okay.
And for nanoparticle, so when it absorbs light, so it heats up, it expands, and this
so
expanding,
acoustic-
yes, just sending the...
But we have different size, so frequencies will be
Yes,
very
so
wide.
it's a good point. So we're actually trying different ways how to unmix the signal from nanoparticles from the signal of biological tissues, and one of the approaches is measuring the frequency of the ultrasound response, and so we can we are trying to distinguish based on the frequency as well as like measuring different wavelengths of excitation or making a non-linear measurement. So we are trying different techniques how to mix the signal.
Any question, Stanislav?
You said about synthesis of magnetic nanoparticles based on gold and ferrum oxide. Did you confirm their magnetic properties by direct measurements of
Yes, we did it.
Magnetic response.
Yes, thank you for your question. So just a moment. I will just come to this slide. So in this paper you can find all the data. So it's here.
Sorry, Visa spectra. I mean vibration magnetometer. I mean hysteresis loop.
It's not on the slide, but in this paper you see that on the bottom.
Okay.
Yes, so
I'll see. Thank you.
Just I don't have the numbers in my mind, so just don't remember them. We measured them, but you can find them.
Okay, any question?
How do you determine the degree of porosity of the nanoparticle from the transmission electron microscopy, and what is the importance for porous titanium nitride nanoparticles? If it differs in absorption efficiency between solid and porous nanoparticles?
Okay, I got your question, but our titanium nitride nanoparticles, they are not porous.
You show the transmission electron microscopy picture. And
this one?
No, and say that it's porous.
Sorry, probably no. They are not porous. So titanium nitride nanoparticles are not porous. So at some exotic circumstances, they can have cavities inside. Like if you ablate this target in hydrogen peroxide. So in this case, we sometimes find like at about probably third of all nanoparticles there are cavities inside. But generally, so they like a solid object. So like here.
Okay, we don't have any time more for the questions. You can speak during the lunch. So we should thank Dr. Popov for his nice presentation. And we will move to the next presentation that will be done by Professor Tarasenko from Minsk, and he's a member of Belarus Academy of Science, and it will be an online presentation, and I hope that our technical support will show us we have a connection. Нету? No contact? Okay. Yes.
Yes, so then we will skip for the next presentation, and the next talk will be given by Ekaterina Barmina. And this is an oral talk, and the title of her talk is Modeling of Laser Fragmentation of Nanoparticles as a Wave Process. So Ekaterina, please, you have 15 minutes, and 3 minutes before the end, I will stand up. So for the technical stuff, this is the presentation number 4. The author is Ekaterina Barmina.
Good morning, my name is Ekaterina Barmina from General Physics Institute, and today I would like to present our new model about the laser fragmentation of nanoparticles that based on a wave process. And this model was developed in a cooperation with Baranov Central Institute of Aviation Motors and Dr. Kulishov. So, why we did it? Because I don't know who is familiar with the laser fragmentation process. Just if somebody doesn't know, I just to say that laser fragmentation process is a process is provided by laser radiation of a colloidal solutions of micro or nanoparticles in the liquids. And if you can see here, anyway, it's a black curve. It's an initial size distribution of a colloidal solution, and after its laser irradiation, we have a different size distribution. So it's a well-known process, and such fragmentation is used to reduce the size of nanoparticles. And till now, we have a different kind of models of formation over the laser fragmentation processes. Some of them, it's a photothermal vaporization, atomistic view of a laser fragmentation, molecular dynamics modeling that will be presented by Professor Stanislav Lukashenko on Thursday, and with a cooperation with Dmitry Ivanov anyway. And also another Coulomb explosion model. All of that model can exist, and all of that describe this laser fragmentation process. But why we did it? Because from our side, from General Physics Institute, we did the experimental data we presented, and our colleague from Baranov Institute did the modeling. And the aim of this presentation, it's create a model that based on a wave process, generalization of a wave mechanism of the process of a laser, comparison of suggested experimental or theoretical data, and so on. Anyway, so what, it's a prehistory, and it was more than 10 years ago. It started from the oxide aluminum nanoparticles that was irradiated by flash lamp, and it was 2 articles about it when the colleagues noticed that the laser fragmentation, it's all the time discussed. If nanoparticles divided or 2 equal pieces, or if we have big pieces and small fragment is detached from that. And it was experimental data. It was small modeling in our colleague started. It doesn't work. Sorry, technical support, please. Anton, I cannot move like that, no? Anyway, so I will start to continue, and it was oxide aluminum nanoparticles with a layer of oxide, and that nanoparticles was irradiated by flash lamp. So what we have, the next slide, is an idea of our modeling at the main slide. I don't know why it doesn't work. But the idea is that when we have it generally, model is universal. When you irradiate the particles by laser, by flash lamp, but you have, for example, have a ultrasound irradiation. The main idea is that when the nanoparticle, we have one big, okay, we see just for one nanoparticle in just modeling now. And when we have a particle, in our case, it's a laser pulse. Nanoparticle absorb the incident laser energy. We have a heating expansion of this particle, and we have an even distribution of the pressure of this particle. And no? Here it works. No. Okay. Thank you. So this here we are. So we have, as I told you, we have a particle, we have a laser pulse, and as we know, under laser absorption by nanoparticle of incident energy, we have a heating expansion, we have a heating of a surrounding media, because usually all the time we work in a liquid. We have a formation of nanobubbles, and Professor Nagamov knows about nanobubbles, everything, and nanoplasma. Anyway, surrounding of particles, finally, we have a bubble, and we have a different pressure between melt, now it's a melt particle, and surrounding bubble. So this is bubble, we have a cavitation, and once this bubble is collapsed, so we have a changing of a pressure. In that moment, we induce the unloaded waves that distract the melt nanoparticle. And in our model, we suggest that our particle is like a resonator, that and the unloaded waves that are formed their frequency depends on the size of this initial particle. So we have a resonator as a particle, and we have a reflective of the uploaded waves from all sides of a particle. So we have an interference that leads to formation of stationary waves. And these stationary waves has the same frequency, and they induce when the bubble collapsed, and it's known here. After that, we have this stationary wave induce the capillary waves. This is the main idea, and these capillary waves are situated on the surface of this nanoparticle, but we remember that nanoparticle is resonated. These capillary waves have the same frequency, but they have a different wavelength. And after that, they interfered with each other. So we have again antinode on the surface of a melted nanoparticles. It's liquid, still liquid nanoparticle. And when it's a maxima of density, we have the small fragments removed from surrounding liquid. So this is, as we see, this is a laser fragmentation. We have, and all the next results, is it clear? No? Because for me, it's the most important things that everybody understood it. Because all of next slides, it will be just a comparison with the theoretical and experimental data. Anyway, so in our modeling, we have tried different kind of distributions, because when we have nanoparticles that generated by laser ablation of solids and liquids, we usually have a wide distribution over size. And this distribution is described in our case by a dispersion. It's a main parameter, and we found that the best modeling, we compared our distribution with the Maxwell distribution, and it fitted very, very well. So, here it's our experimental setup. We used nanosecond laser pulses, and we ablated, we did laser fragmentation of gold, alumina, and selenium nanoparticles. And what about our results? Here you can see the initial size distribution of particles for 3 elements, and after that laser radiation. In all cases, we can see that new peaks appears in small sizes. We estimated a dispersion, and this is parameter K. I forgot to tell you that when we have interference of capillary wave, it can be the different, it can be fragments, it can be formation of fragments with different parameter of harmonics of a capillary wave. It will be, can be first order, second order, third order, and here it's calculated. So it's just experimental data, and applied our model. We can see the final results. Here you can see the dispersion, the theoretical and experimental data, and what we can see with selenium, it's a big problem because we cannot calculate it very well, because here it's a big dispersion, and it doesn't fit, coincide with the experimental data very well. And we discussed about this because I saw you, because we have waves, we have a velocity of sound. Selenium is a semiconductor, and he has a different viscosity. So in and the sound waves, acoustic waves spread there in another way, and we decided that selenium nanoparticles they are no resonated. The main idea is that our particle resonated due to the formation of loaded waves. So here you can see the application of our model, for example, for fragmentation of alumina nanoparticles with different fluence over laser beam that incident to this colloid, and experimental and theoretical data is coincide very well, and also we can see that it's a different harmonics of capillary wave. So here my conclusion, I would like, maybe I'm experimental physics. If you have any question about the equations and so on, I will speak with you during lunch because I have not the time now. And I would like to say that this model also is fitted to, for example, formation of nanostructures by laser ablation in liquids. And in 2 weeks, I will be presented in ultra fast. This is, for us, it's a universal model. So I would like to thank my colleagues, Dr. Alexander Simakin and our PhD student Kuder Aishi for their technical experimental support, and our industrial partner, Pokels. And also, if somebody would like to work in our lab, we have a few vacancies now. We are looking for a PhD or students. It's a General Physics of Institute. You can contact me. And thank you very much for your patience and your attention.
Thank you, Katerina, very much for your very nice talk with a new view on the laser fragmentation mechanism. So we have a time for a few questions. So please.
As a first approximation for me to understand, can you calculate the temperature of the particle and pressure near the surface of the particle? Just 2 figures.
In this model, we just...
No, just in general.
Generally, yes, of course, we calculate all of...
And what, it is not enough, you need capillary waves to apply and so on. Or just if you have boiling, if you produce strong pressure near the surface, it will break. No?
Yes, but you will not have a formation of a... it doesn't enough just pressure, temperature.
That's my question.
Yes,
what is
you
the pressure
need...
and what is the temperature? If they are too small, then I understand that you should apply to more sophisticated mechanism. But if a simple mechanism works?
Look, in our case, when we have the main parameter, it's a pulse energy in the pulse energy and the pulse duration. We need to melt particle. We need to form a nanoplasma, nanobubble around particles. That after that, this bubble will collapse. For pressure, we, for example, in our model, we just calculate the wave process. We did not calculate temperature and pressure, okay? We can calculate the energy that absorbed and what kind of an energy is needed to formate all these waves. This is calculated in our model.
Do you really need melting, for example?
Yes.
Why? You can break solid material in quartz.
Yes, you can
I'm
do.
sorry, colleagues, I need to interrupt you. You can continue
Okay.
after the session because we are out of time. So actually, Professor Tarasenko, he connected. So and now he will give his lecture. And the title of his lecture is Laser Ablation Synthesis and Assembly of Multi-Component Nanostructures in Liquids. So Professor Tarasenko, please. Have 15 minutes.
Thank you very much for introducing me. I'm sorry I did not take into account that time in Samara is different from time in Moscow. We have the same time in Minsk and Moscow, but in Samara the time is different. So topic of my talk, laser ablation and assembly of multi-component nanostructures and liquids. I represent Plasma Physics Center of Stepanov Institute of Physics, National Academy of Sciences of Belarus. I would like to thank organizers for invitation. In my talk, I would like to discuss capabilities of laser ablation plasma in liquid for synthesis of multi-component nanoparticle in liquid and assembly them into ordered structures on the surface. Last years, we studied the relationship between nanoparticle structure and by variety of experimental conditions and found that we can found the condition for preparation of different nanocomposites, such as nanoparticle of alloys, for example, germanium, stannum, germanium tin, compounds nanoparticles such as silicon silicide, oxide, zinc oxide, copper oxide, dope nanoparticles, for example, fizz cobalt or neodymium, and hybrid nanoparticles such as zinc nanoparticles are combined with carbon or metallic, small metallic nanoparticles, silver or copper, and so on. And at the end of my presentation, I would like present our recent results concerning laser ablation and electrical and applied electrical field, because this approach can be used for not for formation of composite nanoparticle, but also to deposition them onto the surface. Some words about the nanoparticle production by ablation in liquids. Advantages, first of all, quite simple preparation process. Sufficient efficiency of this process for preparation of colloidal solution of sufficient concentration, and so on. Its features of this process is well known and discussed by previous speakers. Laser ablation is based on focusing of laser radiation on the target submersion into liquid. We also use in our experiments, this is mechanism of nanoparticle formation in during pulse laser ablation in liquids. Several processes are accompanying action of action of laser beam on to the surface, and main feature is formation of cavitation bubble, as previous Professor Barmina said about this. And two main mechanisms can be distinguished during action of strong laser radiation on solid and liquids. Aggregation of ablated atoms and cluster into small embryonic nanoparticles, and they grow by assembling cluster and attached to free atoms. And the second mechanism, plasma-induced heating and ablation of particulate from the target. Particulate formed this droplet can be released from the molten surface of this solid target. Relative contribution of these two mechanisms determines the final size distribution of the produced nanoparticle. Besides chemical reaction during plasma-induced formation in liquids, chemical reaction can be between target species inside laser-induced plasma, between ablated atoms and surrounding molecule. Also, in principle, 4 different type of chemical reaction can be distinguished during this process, and they can be used in our experiments for production of nanocomposite. As for equipment in our experiments, we use nanosecond laser ablation, neodymium laser, fundamental wavelengths. This you can see laser ablation parameters in our experiment. Besides, we in our experiment we use laser-induced modification when we produced solution and irradiate by addition, usually by the second harmonic of YAG laser in order to change not only the size of nanoparticles formed, but also we use this laser-induced modification to change the inner structure and co-melt if we irradiate, for example, mixture of nanoparticles, different composition. Some example I would like to show in my for next slides. For synthesis of nanocomposite nanoparticles, different ways different approaches can be used. In our experiment, we used, for example, combined approach when we, at the first stage, we proceed, we treat micro powders by electrical discharge in liquid, and then we used laser irradiation of the produced mixture of nanoparticles to obtain, for example, alloy nanoparticles. One of example of this process, of this approach, laser formation, for example, silver copper nanoparticles. We were able to produce using these two stage of nanoalloys, this silver copper nanoparticles at the first stage. As you can see here, we proceed a mixture of conventional silver and copper micropowders by electrical discharge of such configuration, as you can see here. And after that, we additionally irradiate the formed suspension by the second harmonic of YAG laser, and in result we obtain, as characterization of the formed nanoparticle showed, we obtain copper silver alloy nanoparticle. Another example of production of germanium gadolinium silicide nanoparticles. In this case, we used irradiation of mixture of previously produced by laser ablation gadolinium, silicon, and germanium nanoparticles by the second harmonic, and in this case, as results of characterization showed, we were able to obtain gadolinium, germanium gadolinium silicide nanoparticle, which can be used, first of all, as magnetic nanoparticles for hypothermia, so-called self-regulated hypothermia treatment in biomedicine. Laser ablation in colloidal solution or in salt solution, this approach we used for preparation of doped semiconductor nanoparticles, for example, nanoparticles doped with cobalt, or zinc nanoparticle doped with neodymium. This, for example, these nanoparticles are very effective. It can be used in. They exhibit near-infrared luminescence of neodymium ion in the matrix of Zinko and can be used in biomedicine for because in the region of so-called the second transparent region in biomedicine. Sequential next approach we used in our experiment, sequential laser ablation. In this approach, we applied this approach, for example, for preparation on germanium silicon alloy nanoparticles. This is, as you can see here, this is a three-stage process. First, we obtain silicon nanoparticles, laser ablation of silicon target in SNO. Then we ablate germanium target in silicon colloid, and after the third stage, after laser-induced modification by the second harmonic of YAG laser, we were able to obtain silicon germanium alloy nanoparticle. Is characterization for example, by high resolution term we obtain. In this case, we can conclude that indeed we obtain silicon germanium alloyed nanoparticles. Such approach we also use for preparation of silicon silver nanoparticle. In this case, it is possible to obtain silicon nanoparticles accompanied by small silver nanoparticles. We found in our experiments that results of laser ablation, morphology of nanoparticles, is dependent on the profile of intensity distribution cross section of laser beam. We used for ablation so-called not only Gauss beam, but also Bessel and annular beam. In the case of annular beam, we can obtain quasi-spherical nanoparticle, but in the case of Bessel beam, such long filaments formed in colloid after laser ablation. Another example, shortly, we obtain hybrid cerium oxide nanoparticle. In this case, by using a three-stage approach for formation, we can obtain nanoparticles of different morphology, as you can see in this slide. And these nanoparticles antibacterial activity against different bacteria and can be used. Besides formation of nanoparticles, it is very important to produce to deposit or to produce surface layer with these nanoparticles, because for different practical application is required. For this, we developed two approaches. First, deposition. First approach is based on action on the layer. For example, as you can see here, C-target, silicon target, we deposit by pulse laser ablation deposit a thin layer, a thin film of tin on the surface of silicon particle, and after laser irradiation, in liquid, we can obtain such structures of different morphology, and our goal was try to obtain silicon tin alloy nanoparticle, but now this experiment are in progress. And another example, when we colloidal solution deposit using a traditional deposition methods such as spin coating or blade coating, and irradiate this layer on the surface by laser, we were able to obtain, in result of local heating, and we were able to obtain doped zinc cobalt nanostructures on the surface. This result of examination of the layer produced by laser radiation of C-tin composite in liquid. And at the end, finally, I would like to present our recent results concerning laser ablation in applied electric field. As you can see, when we applied electric field to the target, in this case, we found that nanoparticle of different morphology can be produced independence on the applied voltage. This slide illustrates this. This is morphology of nanoparticle formed by applied, for example, 50 volt to the zinc target, and this slide illustrates when we increase the applied voltage to 200 volt. And we use now this method, this approach for preparation of zinco carbon nanostructures. In this case, we produce zinco nanoparticles in colloidal solution of carbon, and we found that in this case we can deposit during this ablation not only zinco carbon composite nanoparticles are formed in solution, but also they deposit on the cathode, on the surface of this substrate, which were submerged into the liquid. So, in my conclusion, several types of schemes were investigated, and the capabilities for preparation of different type of nanocomposite were studied and demonstrated preparation of different nanoparticles, nanostructures of different morphology. We collaborate with different organizations, and I would like that we continue our collaboration with Professor Barmina. Thank you for your attention.
Thank you, Professor Tarasenko, for your presentation, and we have time for one short question. Are there any? Okay, one.
Sorry, I have a question. Nice to see you, Professor Tarasenko. I would like to, anyway, nice to see you, Professor Tarasenko. Greetings to Natalia. And I have a question. Have you tried to do multiply nanoparticles that it's a composite that consists of, for example, 3-5 metals? It's a new trend now. Professor Barchikovsky told me about it. We didn't try, but maybe you tried. You have tried.
Yes, we try to obtain, for example, nanoparticles alloy of copper and silver in our experiments. But as for 3 metal nanoparticles, it is possible using laser ablation approaches in liquids, but our recent experiments were directed to preparation, for example, silicon nanoparticles, basically.
Okay. So
Called metal semiconductor nanoparticles, but to prepare alloy of metallic nanoparticles, it is
yes, as, if
possible.
you know that our friend, our colleague from China did it. For example, he did the composite nanoparticles that have 5 elements, and they have 5. Yes, and it's if you want, I can send.
It's
interesting. Yes,
Yes.
it's nice because you should confine all the crystalline structure that everything was work. Anyway, yes. I give you an idea, why not?
Oh, yes, thank you, Katya, very,
So
very
greetings to Natalia, yeah, thank you.
Okay, thank you very much, Professor Tarasenko, for your presentation. And we are moving to the last talk in this section. And this presentation will be given by Kirill Kharkov from Vladimir State University. And the title of his presentation is Laser Ablation and Fragmentation of Nanoparticles in Liquid, Electrostatic and Magnetic Fields. So Kirill, you have 15 minutes.
No, I don't see presentation. Yes. Okay. Hello, everyone. My name is Kharkov Kirill. I am from Vladimir State University, and I want to show our experiments and our experience in laser ablation and fragmentation different materials. I have a 3 parts of my talk, and I show you how we obtain nanoparticles in liquids, in electrostatic field, and in magnetic field. First of all, I need to show our equipment. It's from laboratory femtonanophotonics in our institute, and we have a terbium femtosecond laser system from Avesta company. Its wavelength about 1 micron, pulse duration about 280 femtoseconds, and pulse repetition rate up to 10 kilohertz, and we can change it. And what we do, we made a real laser complex with different parts of supplied elements. We have a laser, we have cameras, we have translations, and galvanic scanners, and other parts of our system. And we made our program software to operate this laser complex, and it very convenient, and we can precision processing our surfaces, or we can do different experiments. And we can see online what happens in our laboratory in real time. First of all, it's about laser ablation and fragmentation in liquid media. We can see the schematic scheme of our experiments. We have a cuvette where we put our target, and after that we made laser ablation, and if we need, we produce laser fragmentation. And one of the part of this scheme, we control our temperature of our colloid. It is important. First step, we made laser ablation. After that, we made laser fragmentation, and can use many different materials, from titanium, from zinc sulfide and other sulfides, for example, wolfram and molybdenum. We can see the particle distribution of our particles and optical spectra of these colloids from molybdenum disulfide. And we can see how our samples from laser ablation and laser fragmentation from 2 minutes, 40 minutes and 1 hour. We can see the color of these samples changes. Also, these experiments was in ethanol. If we use the water as a medium, we don't see change in color, but we can see that our colloid more is not so dark, and we can see the optical spectra of these samples. On these graphics, we can see the change in optical spectra with different laser fragmentation. We can see the from 10 minutes, 20 minutes, and to 1 hour, and with different dates. For example, on the last picture, we can see that optical spectra is changed in time. We can produce different particles. For example, it is TEM image of our particles, molybdenum disulfide. We can see small particles with core shell, sometimes structure. When we use laser fragmentation in ethanol, we can see the change in color, and we see that the structure of our particles is also changed. This also optical spectra, absorption spectra of our colloids, and Raman spectra of our samples. Also, we use wolfram disulfide for nanoparticles, and this also optical spectra with different time fragmentation. We can see the change in optical spectra, and its spectra in ethanol media. We can see also change in our absorption. And these spectra from disulfide of wolfram. When we use laser fragmentation with large time, we see that we have not only the sulfate of molybdenum, but we produce the molybdenum oxides. And we can see it on the last sample with blue color, and we can see the chemical reactions what be in what when laser fragmentation is a long time, for example about 1 hour, we have small particles, but sometimes it is not an initial material, and we have a suboxide of our initial sample. For example, we have the part of sulfate particles and oxide particles. Also, we obtain the photothermal characteristic of our colloids and see that we have a good absorbance at 600 nanometers. It was first part about laser ablation in liquids, but second part, it's ablation in electrostatic field. You can see our experiments. We use a galvanosconator, 50-second laser, a vacuum chamber with gas argon, and it is schematic representation of our experiment. We can see the chamber, we can see the sample and electrodes on different parts, and this also is a representation of the processes which going in our place. We can see it is experiments with zinc sulfides. We can see 2 electrodes where our nanoparticles deposit on these plates, and after that we can take these plates and make a colloidal solution, for example. But if in first part where we can produce oxides particles, in this part we have a change in phase state our particles. For example, we can obtain zinc sulfide nanoparticles in sphalerite form or, for example, wurtzite form. It is a electron microscopy image of our particles with small size, and this is photoluminescence spectra of our deposits zinc sulfide nanoparticles. And the third part, it is laser ablation in magnetic field. We made a new camera and put in our camera magnets, neodymium magnets, and also produce laser ablation, and our particles deposit on our plates in camera, and after that we can collect our particles and analyze it or make a colloid solution, for example. It's also in gas argon with oxygen, and we can make different types of particles. For example, we use iron initial material, and if we change our parameters of experiment, we can make iron particles or oxide iron particles with different phase states. That's all. Our conclusion that we can use different materials, we can use different techniques from pulsed laser ablation in liquid, in electrostatic field, or, for example, magnetic fields, and obtain different nanoparticles with different size and their physical chemical properties. Thank you.
Thank you very much for your presentation. We have time for several questions. And yes, please first.
I don't understand. Well, you say about vacuum camera, but after that you put a
sorry,
pressure.
yes, not vacuum, with gas, yes,
with gas.
With pressure.
But
sorry.
how large pressure is? 10 atmosphere?
Not
1 atmosphere?
Yes, about.
So small.
In different experiments, we use different pressure.
And how you collect with nanoparticles?
With particles.
We have a large velocities. Expansion velocity. In
gas, our nanoparticles deposition on electrode plates, and after that we take our plates and with.
So they are charged. The particles, nanoparticles, are significantly charged. If the electric field influences. Yes.
Okay, I have one question about fragmentation of molybdenum disulfide. Can you get these blue colloids in water when you make fragmentation in water?
If we have like a suboxide of molybdenum.
So, but experimentally, did you obtain it only in ethanol or in water?
In our experiment, we obtain blue colloid of molybdenum only in ethanol. In water, we don't obtain it.
And if I understood correctly, you attributed this blue coloration to oxidation of molybdenum.
Yes, if it is blue color, we think that we have suboxides of.
But in water, the oxidation should be faster, and you should also get something like this.
There are a lot of oxide of molybdenum, you know.
It's just different.
Yes.
Okay, thank you.
And some of this picture, I think, made in your laboratory.
Yes, because it's very tricky to get this blue coloration of this type of nanoparticles. Yeah, I just was curious. So we have time for one more small questions. Is there any? Okay, if no, let's thank the speaker again. So, and now our second session is over, and we have lunch time, and the next session should start at 2:30, so you have some less than 90 minutes for your lunch. Thank you to everyone for participating.
Раз-два. Никита, здравствуйте. Так.
Здравствуйте. Меня слышно? Прекрасно. Да, в этой секции он второй. И у меня вопрос, как я презентацию демонстрировать? Я ни разу не пользовался.
Все вывел. Все вывел. Работает. Да, да. Скажи ему, что кликер находится не в той стране, а в моей стране. Да. Все ли хорошо? Сработало, да? Ну, хорошо. Я сейчас еще выставлю iPad на столик, чтобы вам было удобно, чтобы вы не смотрели на экран, а смотрели в iPad.
Session of laser matter interaction, and my name is Sergei Klementov. I am from MIFI, and my colleague from Moscow State University, Fyodor Potemkin, we are chairing this section. And the first talk will be given by Fyodor Potemkin, which is called Laser-Induced Extreme State of Matter in Silicon, the way to create and to diagnose. Please, Jan.
Thank you, Sergey, for this kind introduction. Thank you, program organizing committee, for inviting me to this conference. For me, it's a great honor to be here as an invited speaker. My today's talk will be about the laser-reduced extreme state of matter in silicon. This is my paper outline. Okay, sorry. First of all, I'd like to say general words about how to create the extreme state of matter in solids. Then I want to specify what is the problematics to reach these conditions in silicon. Then I go to presenting approach which has been reported yet for deposit energy density increase in silicon. And then I go to our results, presenting bulk modification of silicon using mid-IR laser pulses and two-color excitation. And if I have time, at last part of my talk, I want to present the preliminary results of time-resolved diagnostics of phase transitions in silicon. And then I want to conclude my talk. In general, tight focusing of your laser radiation, femtosecond laser radiation with a microjoule level of energy leads to the intensities of 10, 12, 10, 13 watt per centimeter square in the laser beam waste. So the initiation of ionization process leads to microplasma, which is formed with the electronic density close to the critical one and the temperatures for about 10 EVs. The relaxation of such a plasma on picosecond time scale leads to energy transfer from electronic to ionic subsystem. You have the conditions for shock wave generation with the pressures on the front much more than the Young models for the materials, so you have some kind of the extreme state of matter formation, which could give you the micromodification information as a result. One of the most important parameters, this is the deposit energy density, this is the absorbed energy per volume, and so tuning this parameter, one can reach the specific regime and PT diagram of the material. So this is the route for new phases and novel technologies for optoelectronics and also for reversible and irreversible phase transitions, which could be the basis for novel devices, as in the recently paper of the Vitaly Konov group. So it's really principle to optimize, to control, and to increase the deposit energy density. In silicon, we have some problems with this because the high refractive index gives us that your laser energy is distributed along the channels much more than the beam waste. In near infrared, 2-photon absorption give you the plasma, which is formed across this region, and so the plasma defocusing leads to the delocalization of your femtosecond laser energy and to lowering your DED. Making impossible to provide the permanent damage of your material. So in our case, the goal is to create single-shot bulk modification inside planar C because it's the technologically interesting task. So we want to develop experimental methods for DED measurements and propose and plan the techniques to increase DED and to retrieve the dynamics of laser matter interaction in semiconductors using silicon as the example. Here you see the approach that is currently realized. First of all, this is hyperfocusing using the microspheres from silicon. One can overcome the problems with the high refractive index, and so just shrinking the region toward the focus. But the 2-photon absorption, which is in infrared, is quite high, as I say, leads you that very low delta N when you just work in one pulse regime. Shifting your laser wavelength to 2 microns, can you give some kind of the increasing of this delta n? But picosecond pulses that it was used in such paper gives you the weakly deterministic nature for laser-induced damage because of lack of seed electrons. Your ionization process is ineffective for this wavelength. This problem can be solved by using imperfections of your contrast of your laser pulse, because you have the nanosecond pedestal which could work as the seed electron generator. But the more powerful way is to use 2 pulses, which was extremely successfully realized in our group using we use it for modification of dielectrics. So the novel concept which I want to present you is tightly focused mid-IR laser radiation and 2-color excitation. I want to say a few words about our experimental setup. We have lots of femtosecond sources, gigawatt power level. This is home-built sources, and I'm proud of this. Some of these sources have no analogs in the world. For instance, CPA system femtosecond based on iron doped zinc selenide, which provides the femtosecond pulses in 4-5 micron range. Using these sources and using the very effective conversion schemes, nonlinear schemes, give us to obtain microjoule level over a broad range from UV to terahertz. So this is the perspective of this work in multispectral, multi-pulse excitation of solids. Here you can see the single color scheme. Here we use we tightly focus our laser radiation into the bulk of the silicon. We use the high resistance silicon in order to decrease the effect of the defects, which are also strongly depends on the laser-induced damage processes. We monitor the incident and the transmitted energy through the pulse, also on the third harmonic, which is generated on electrons, on structural changes, on phonons. It's really a highly sensitive tool, so we use it for all of our experiments. In 2-color scheme, we just can add the another color and combine it collinearly and tightly focus this radiation to the sample using the refractive object in order to avoid the spherical aberrations. Here, the method we use, all the experiments has the full support of the numerical simulations, which provided by our colleagues from the Kurchatov Institute. The initial stage was modeled by the propagating effects was modeled by the unidirectional pulse propagation equation, and the deep insight into the physics of the population dynamics in conduction band, we used the multiple rate equation and the extended multiple rate equation, which was proposed also in collaboration with this team. To diagnose the process of micronodification formation, which is taking place on picosecond, nanosecond time scale, we use the molecular dynamics and 2-temperature model. In order to, in experiment, to measure the DED, we use the absorbed measurements. So this is the standard scheme. It's like some kind of nonlinear transmittance, which gives you the absorbed energy. And the more difficult part is the interaction volume, which strongly depends on the laser intensity, wavelengths, and duration. So there are lots of methods which we propose: 3D propagating imaging, plasma luminescence, and the third harmonic also imaging. And the third harmonic is the most powerful and sensitive, because it strongly depends on stationary delta n and dynamical processes, which can be related to also to the polarizability changes or Chi3 changes. So it's extremely sensitive and can be applied for any time scales from 100 femtoseconds to nanoseconds. It was successfully, there was some successful realization in cell tracking, library and imaging, 3D optical storage, also with 3D imaging, and also in our group for microplasma and micromodification diagnosis. We start with the near-infrared excitation of silicon in order to obtain the information what is the maximum DED we could achieve in near-infrared excitation. We just see that that our area is strongly delocalized. As you can see from the left part of the slide, this is the how the interaction volume changes with the energy. So it gives us that the much more energy. This is the blue curve on the first in graph. We have only 10% of the energy after the excitation. So we try to increase this, the electronic density and the DED using the chirping of your pulse. It's really simple idea, because when you chirp your pulse, you just decrease the intensity, so you can just transfer much more energy to the focal volume. And so this is why our DED increases up to kilojoule per cubic centimeter, but this is not enough to obtain the permanent damage of the silicon. So we go to the mid-air. From the first view, it's not trivial, because when you just shift your laser to the laser wavelength to the mid-air, you have the problem with the critical density of electrons, which is lowered as the inverse squared law of your wavelength. So you have the problem with the decrease of N2, which helps to self-focus your laser beam for 2 micron pulses. But another more deep insight in this problem give us that nonlinear figure of merit increases because of a decrease of 2 and 3 photon absorption much more than the decrease of N2. And another point is the hitting electrons is due to the much more pronounced Pandoramet effection of the mid-air laser pulse, give you the opportunity to accumulate in your electronic system much more energy. And so we realize this. You see here how the DED increases up to 5 kilojoule per cubic centimeter for using the tightly focused mid-air laser pulses with a wavelength of 4.6 micrometers. It is quite higher than the DED, which is needed to melt and to heat and melt the material of silicon. Another additional improvement of such high DEDs, this is the morphology of the defect, which is registered by the ferrharmonic microscopy, and also using the elimination of this modified area by 1.4 micrometer laser. We just you can see the ring over the center. This is the origin of the laser-induced shock wave, which is just expand from the locally deposited energy of your laser pulse. So we register the modification with the micron dimensions up to the 125 micron below the surface, and this is single shot regime. I want to skip these slides, but this is some kind of the very deep physical insight and why such high DEDs can be realized. We just try the standard multiple rate equation model, and it gives us no improvement of this high value. So we propose that it's because the critical level where the electrons become to gathered because of the one photon absorption is much more than the impact ionization rate. So we just add another level just to increase the thermal energy of the electrons, and so it gives us the possibility to, as you can see at the right corner of the slide, to enhance the mean energy of electrons, and so we increase the DED to the DED in our theoretical, our numerical simulation to the DVD value, which is which was obtained in our experiments, and so this proves that the heating mechanism is principal for mid-infrared optical breakdown. In order to prove that we can provide the microwave formation, we just modeled this process using the molecular dynamics. As initial condition, we use the DED and the electronic temperature, about 3-4 EVs from the simulations which we realized previously. And so the results that the micro modification which we see, this is the void in the ring, void in the right corner of the slide, this is the black area where the no atoms we see, and the ring, white ring, this is the amorphous phase. because we could using the molecular dynamics, after some procedures, obtain the information what is the phase here, and this is the amorphous phase. If one want to more accurately control the process of excitation in order to minimize the energy you use, in order to control more precisely this process, and perhaps lower your numerical aperture for your focusing, one can use the two-color excitation of solids. This concept was for the first time proposed by Alexander Mikhailovich Prokhorov, Modest Fedorovich Koldunov, and others in Prokhorov Institute. For nanosecond and picosecond pulses, we just extend this concept for femtosecond pulses, and we have some kind of very good realization for the dielectrics. The expansion for solids is the following. You have the two pulses. Both pulses have the intensity much lower than the plasma formation threshold in order to not to include the ionization process in the propagation of your pulses. The seed electrons, the short wavelength pulse give you the seed electrons, and the long wavelength pulse just increase the mean energy and via the heating mechanism and its concentration via the avalanche if it's possible. Keeping these electrons localized in space, you can just increase the electronic density of your electrons up to the values which is enough to phase transition to be occurred. And so this is the concept. And what are the results with two-color excitation of silicon? You see, this is at the left part of the slide. This is the single-color excitation using the 4.6 microns and 1.24 microns, but using not such high NAs as the previous slides, but also only NAs with up to 0.5 value, because we have such kind of reflective objective. We see that for single pulse mid-IR excitation, we have the 3-4 kilojoule per cubic centimeter, which much less than the threshold DED, which we need for permanent damage. For near-infrared pulse, we see the flat dependence of your D as a function of energy due to the delocalization effects. But when we mixed these two pulses, we see the twice increase of our DED compared to the single mid-infrared pulse, reaching this 7-8 kilojoule per cubic centimeter. So it's quite prospective for technological tasks because this could overcome the spherical aberration, which can be when you just focus your laser radiation using the such tight focusing regimes. And the last point, this is we retrieve the phase transition, which for these aims we use the coherent phonons as the indicator. The coherent phonons are generated when the energy from electronic subsystem goes to the ions. So the atomic displacements could lead to phase transitions, and due to the bonding between the atoms also change, so with the phonon spectrum changes, and so this is the idea how to probe these phase transitions. We use the nonlinear palm probe, which was proposed in our scientific group, using the ferrharmonic, which is generated on structural changes. After the time domain Fourier analysis of this signal, we can obtain the frequency as a function of time, and you see some kind of the more pronounced frequencies in this signal. Some frequency can be simultaneously in time. So because we know the phase diagram of silicon, we can just put the dotted line in each time position where some kind of the novel frequencies are appeared or disappeared. And after that, when we just put this certain times with the pressure, because we know that the phase diagram of the silicon, we have the exponential decay, so it indirectly prove our idea that the coherent phonons can work much well for these aims. So this is all, and I want to conclude my talk. We create the single pulse microvoids in bulk of silicon. We propose two concepts to increase the DED two-color concept and tightly focused mid-IR laser pulses. We prove using our theoretical numerical simulations that the strong heating is crucial for silicon bulk micromodification in mid-IR. And so we have the preliminary results on coherent phonons, which can give information about the sequence of phase transitions, and our atomistic study prove the microvoid formation inside silicon. So this is, thank you for financial support, and thank you for my colleagues which could provide the numerical simulations, and thank you for your attention.
Thank you very much, Professor Potemkin. Are there any questions, please?
Thank you very much for your beautiful presentation. Indeed, it was interesting. But I'm sorry, Andrei Rode did it maybe 20 years ago, many fast, up to silicon 26 or something like this. Is it still, you don't mention? Because maybe it is wrong or what? What is the reason? And the second one is about the molecular dynamics is too small. It is just, your void is up maybe few nanometer, but you say about micron large cavities. So how? It is 3 orders or maybe?
Okay, thank you, Nail, for your question. About the phases in silicon. We not solving the task of this stage is the preliminary results how we can use the optical methods to diagnose the phase transitions. Okay, because there are a lot of X-ray methods, some kind of EXAFS methods, for example, time resolved, which now are very good working when we use the X files in the world. So this is some kind of the preliminary results. You know that the question for silicon phases, stationary phases, is okay. Yes, you know that there are a lot of phases, but when you have the condition of the dynamical loading, when you just when you have the shock wave which propagates inside your medium, there are a lot of papers in Nature dated, I think, 222, 223, when the people see that the lowering conditions of the phase transitions, because all the points in pressure and in temperature are well known, but they see that these values become slower, and so the question is open. What are the real transitions in pressure and temperature will give you these phases? Maybe in other phases can be, because the question, what is the phase in such non-stationary conditions? What is the phase transition? And so I think in stationary conditions it's okay, because you have the diamond anvil, you have the temperature camera, you can just thermodynamically realize the conditions of just very stational process and very gradual transition from one transition to another. But in dynamical, under the dynamical loading, under conditions of the shockwave propagation, the other things can be. So we are trying to search this new physics. Okay, it's open question. And the second one about the molecular dynamics. Yes, I agreed with that the problems with the few atoms is really a problem for molecular dynamics to be coincide with the experiment. But this dynamics for us needed to obtain the information about the conditions of microwave formation. So we want to see this process because we just have a doubt that this is not the void. And so this is why we just try to use such kind of the modeling.
You have to go fast, Professor Konov.
As far as I remember, at least it follows from our experiments, that major factor which prevents you from heating well silicon is scattering of light by highly ionized material, by multiphoton ionization. And so your major point is that when you shift to longer wavelengths, then you can diminish this effect, and that's all. You just use the longer wavelengths, so the negative lens is not so strong. That's all.
Yes, yes. 2 and 3 photon absorption becomes lower.
Yes.
So we work with the multi-photon absorption.
Because in your discussion, you never mentioned scattering, beam scattering by highly ionized media.
Could I possibly also ask? So you're analyzing energy deposition contributions, yeah, from different mechanisms of absorption. You listed many of them, but in fact, this process, it has stages. So one mechanism are more important at the beginning, and when the others cannot start yet because we do not have a significant amount of electrons in the conduction band, anything like this. Did you analyze it in terms of kinetics?
Yes, thank you, Sergey, for this question. We analyze this in terms of kinetics in our numerical simulations. We have not a long time ago the published paper where they just see have shown the kinetics, what the process which are in the initial part is dominant, where the heating mechanisms or avalanche ionization becomes more important. So we on the way to just to make the deep insight in these mechanisms.
And especially it might be the case of two-color excitation, especially if one is going first and the second is coming later, because you can create the condition for absorption via the second pulse. Okay, any more questions? It's a difficult choice because we are running a little bit late. So let's switch to the next presentation. Thank you very much, Fyodor. The next one is given at a distance by Professor Toropov from United Kingdom, from Exeter, which is called light matter coupling in optical microcavities. Our technical team is ready to, okay, great. So we give you the floor, Professor Toropov. Please start your presentation.
Hello, can you hear me now? Hello? Can you hear me?
Yes, we can.
Yeah.
Please continue.
Okay, that's great. Thanks for a very warm introduction. I'm not a professor, thank God. I'm Nikita Toropov, research fellow from the University of Southampton. At the moment I work here, but this work has been done at the University of Exeter in the close collaboration with Professor Frank Fulmer and also with ITMO University, Miss Kurasua Camilla. Here is the University of Exeter. If you're going to visit it, it will take you 2.5 hours from the Paddington Station from London. I'm going to be talking about optoplasmonic biosensors. So in my title, you can see high power, but it's not like 10 to the 10th or 10 to the 12th, not femtosecond lasers. But anyway, I'm going to mention lasers and nanoparticles as well. First of all, let me introduce microresonators, which can be used for biosensing. They were described by Lord Rayleigh about 100 years ago, a little bit more. There was an observation by Lord Rayleigh when he stands on the dome of St. Paul's Cathedral in London, and if you say something at this point to the wall, this acoustic wave will propagate around the circumference, and if you're standing here, you will clearly hear what this person was talking about. The same phenomenon we can observe in the optical world when we have microresonators made of microsphere shapes or microtoroids or so-called bottle microresonators. They have outstanding values of quality factors reaching 10 to the 8 even in not in the clean room conditions. That's why they're very sensitive to the smallest perturbations around. To describe these perturbations when you're testing single molecules or single viruses, there are two ways of description. First of all, is mostly related to geometrical optics, where changing of the path length for this optical whispering gallery mode, you will change its frequency. The second mechanism is mostly related to changing polarizability of this object under test when it's around the microsphere. Microsphere, of course, this wave propagates due to total internal reflection, but anyway, we have evanescent fields here. They are non-propagating, but they can sense the changes of the refractive index of the around media, changing their polarizability. In experiments, mostly we detect changes of the wavelength of the resonance, which is presented here, and also full width at half maximum, which is presented on this picture. If we have scattering or additional channels for losses under sensing, it may allow us to detect if they are molecule or not. First of all, I'm going to present sensing of big objects. We used a tunable laser, 642 nanometer. It can be also used 780 nanometers. Not that complicated optical systems to collimate beam to make it tightly focused, and we use prism coupler. Prism coupler forms a evanescent field here, and this field penetrates inside the microsphere. Microsphere was preliminarily fabricated by melting of standard SMF28 optical fibers used for telecommunications. The melting was performed with a CO2 laser 10.6 microns. When we send the light from this tunable laser, we measure, in fact, the transmission of this system, and we observe resonances excited inside the whispering gallery mode as it dips in the transmission spectrum. So this is a level of unit, and this can be 20% and up to 40%. When we're adding molecules or any objects under test inside a PDMS chamber, we're expecting to change the frequency of these resonances or their full width at half maximum. First series of experiments have been done with adenovirus. That was work was very great of importance a couple of years ago, maybe 3 years ago, when we had a lockdown related to the coronavirus outbreak. And we also tested that we can sense a single particle of adenovirus. Adenovirus is quite interesting virus because it was used as a vector to develop Oxford AstraZeneca vaccine. And also it has a similar structure to coronavirus with these proteins outside and even the similar diameter. So the basic principle of our device is quite simple. We have PBS buffer, we have solutions of these killed viral particles, and we're modeling fundamental mode of whispering gallery modes inside the silicon microsphere of a diameter of 80 microns. When viral particle is somewhere around, we observed changes of lambda, the resonant wavelength, and we also call it kappa. It's full width at half maximum. But when the virus is attached to the microsphere, we can see permanent shift changes of frequency, and we can see changes of full width at half maximum. As soon as these particles are quite big, they induce new scattering mechanism and reducing quality factor of the whispering gathering mode. Why we call it big objects? Because hundreds of nanometers. To detect single molecules, in fact, you can be quite lucky and detect single molecules with such systems. However, the main drawback, despite the high quality factor, the main drawback of whispering remote resonators is their extremely big effective mode volume. So if you consider it for 780 nanometer radiation, effective mode volume will reach roughly 1000 cubic microns. That is not acceptable. So you have such huge mode which is circulating around your microsphere, and the object under test is somewhere here. The original solution for this was proposed by several people, including my co-author Frank Forma from Exeter. They proposed to introduce gold nanorods as soon as they support plasmonic oscillations, and they can act as plasmonic concentrators, significantly reduce the effective mode volume by like 3 orders of magnitude. At the same time, they spoil quality factor, but not worse than 10 times. So to create real single molecule sensing, we need to attach several gold nanoparticles to the microsphere, and it will eventually improve the figure of merit of the sensor. But the principal scheme is the same. We use tunable lasers, optics, and we record the spectrum, transmission spectrum. So we have done our experiments for such a lovely molecule. It is called 3-phosphoglycerate kinase, or 3-PGK. We fabricated 80 micron sphere. We attached 5 to 10 gold nanorods with localized surface plasmon resonant at 780 nanometers, which corresponds to the wavelength of the laser we use. We attach some linkers to make selective binding linkers. It's a special agent for specific binding. They contain nickel because one of the amino acids of this protein has very good attachment to nickel. And we started to measure our transmission. We actually started to follow our resonant wavelength. So when we have an attachment event, we have changes of the wavelength of the resonance, whispering remote resonance. And the novelty of this work that most of people are trying to make this experiment with less perturbation for molecules, because organic molecules, you can easily simply destroy them. And people are normally working within microwatts and trying to make it nanowatts, but we didn't care about it, and we tried to increase power a little bit. And we found out that interesting peculiarity when people work in these low intensities of whispering remote, it's actually intensity calculated on the tip of the nanorod. You observe positive wavelength shift, everything is fine. Your polarizability is changing, everything is good. But when you increase this power, increase the power of this laser, you simply will observe something different. You will observe negative shifts or blue shifts. And we observed that when we're increasing intensity, we're observing negative wavelength shifts. And eventually, this part 4 of the diagram, it's destruction of enzymes. So we do not consider this area because it is less interesting when object under test is dead. But we consider these 2 areas because this mechanism is called reactive sensing. Everyone is using it, but we have to explain this area now. So to investigate it, we decided to measure it in more details. We actually started to measure not just wavelength shift, but also changes of the full width at half maximum. And we realized that effectively wavelength shifts can be about 0, but at the same time we have a slight increase of full width at half maximum. That means that additional channel of losses like radiation and non-radiation losses from whispering gallery mode is introduced now. And when we increase the energy, when we increase the intensity, we observe even more negative shifts. So, and this additional channel, according to our suggestion, was related to absorption, but it was quite unusual because normally enzymes like 3-PGK or ADK, they don't have absorption bands in the near infrared. Most of their absorption bands are related to UV range. And we decided to add a simple experiment to make a conjugation of 3-PGK with an organic dye, which is called Alexa. There are actually a big family of these organic dyes, and we have selected especially for our experiments Alexa, which absorbs at 780 nanometers. And when we observe wavelength shifts, so we registered that 3-PGK and 3-PGK Alexa gives kind of similar results. So there was a small confirmation that absorption is involved somehow. After that, we demonstrated the same experiments for different enzymes, adenylate kinase. It was also done with the same kind of microsphere, same gold nanorods, a bit different binding. And we realized that when we have pure ADK, it's presented like blue circles here, pure ADK molecules, they do not demonstrate negative shifts. While when we make conjugation of ADK enzyme with same Alexa molecules, we may observe negative shifts. And so the ruling mechanism apparently is absorption. We tried to compare ADK enzymes and 3-PGK enzymes. Like enzymes are proteins, and proteins consist of different amino acids. We realized that the 3-PGK includes 2 amino acids which are called tryptophan. And tryptophan is quite strange amino acid because in the presence of gold nanoparticles, it makes unstable complexes that may demonstrate absorption at these wavelengths like 539 and 785. They correspond to different modes of the gold nanoparticles. This is longitudinal mode and this is a short wavelength mode. So when we introduce 3-PGK molecules without Alexa, tryptophan forms these bonds and we may observe slight absorption. So now we confirm that we have data with Alexa, we have data with tryptophan, we're quite sure that we have absorption of energy, and we can build our model which shows us when we have attachment events of our molecules under test, they absorb energy. They almost cannot, due to non-radiative relaxation, they almost cannot give us quanta as a fluorescence because of metal quenching and many different factors. So all they do is they transform energy into heat. It's a small portion of heat. Heat causes changes of local refractive index, and for water, it is negative. And negative changes of refractive index, local change in refractive index, it is somewhere here. It causes changes of wavelength, which are also negative. So that's why we need to consider not just the changes of polarizability, but also changes of temperature. So the complete diagram of intensity dependent of the plasmonic sensing was obtained. It reveals a new sensing mechanism, which we call top sensing or thermo-optoplasmonic. And a physical model of the plasmonic was proposed. Thank you very much for your attention.
When you excite the Vespel modes using prism coupling technique, what is the efficiency of this process? I mean, in other words, how deep are the M lines? And
it depends on how lucky you are, how good you are in fabrication microspheres. But the most value will reach like 50%, I guess. But normally it's within 10 or 20%.
Okay, and if we consider the other geometry, for example, integrated optics like ring resonators and optical waveguides, can you compare the sensitivity of these two approaches?
Yeah, sure. You can compare them, then it's quite advanced at the moment. But the thing is, the fabrication precision for microring resonator has to be really high. When you make a resonator by melting, it has ideal spherical form and it has ideal roughness. Roughness was one of the main problems. But when you try to make this integrated, like toroidal ones, so you normally need to use etching processes, and etching is destroying quality factor. So there are several techniques to make it smooth, but they're not that great at the moment.
Thank you. We have time for one short question, please. Yeah.
Nikita, thank you for your talk. I have a question about the specificity of your analysis. Your method is quite sensitive, but how do you provide selectivity in real biomedical applications? Is it possible?
Because you mean selective binding of molecules?
For example, if you study a mixture of proteins, will your method be selective?
Yeah, but it of course depends on your mixture, because if we have, for example, mixture of 3PGK and ADK, we definitely will select them because we cover our microspheres with nickel sulfate, and nickel sulfate will react only with 3PGK and will not react with ADK. But if we find something different which will also be reacting with nickel, it's going to be problematic. But normally, all such kind of problems are related to chemistry and surface chemistry.
So what I was talking about, is it possible to make something like ELISA assay to construct a sandwich of several proteins and sense this?
I think so, yes, I think so. Well, I never tried, but I think it is possible.
Okay, thanks.
Thank you. So let's applause again to our lecturer, to our presenting author. So we are coming to the next talk, and I will give the role to Professor Potemkin.
Thank you very much, Sergey. My pleasure to present the next speaker. The talk titled
Sorry, but I cannot hear you.
Support team?
I guess there is some problem.
Do you hear us? No?
I can see you. I see you
hear me?
Talking, but I cannot hear you.
Okay, supporting team, please.
Probably something into the... Let me see if I am on with my microphone. Yes, I do.
Now
can you try to talk now?
Can you hear us?
Ah, yeah, yes, please. Okay, that's great. Thank you.
Okay,
I'm
good.
sorry.
Good. And my pleasure to present the next speaker. The talk is titled Ultrafast Conductivity Control and Commensurate Crystals. This talk was given by, will be given by Dr. Bachetot from l'Instab Paris, France, s'il vous plaît.
Thank you very much. So, can I share here? If I share the screen, let me see if you can see the slides. If I share the screen, do you see?
We
do you see the slides? Okay.
We see.
And if I put it like this, you see even better.
It's good.
Yeah. Okay. Perfect. So I can start. So okay. So first, thank you very much to the organizer for inviting me at this conference, and I'm very sorry to be remote. I hope next time I will be able to have the possibility to join you there. So today I'm going to talk about some recent work we have done on the ultra-fast conductivity control by femtosecond laser. But first of all, let me probably give you, let's say, a broad introduction to this subject. You all know that our society is really deeply connected today to the electronic devices. So basically, many things we do today, it really depends on the electronics, the computer, the mobile, even cars, flight, and so on. So there is a really a ride to try to increase the speed of the electronic. And of course, increasing the speed of electronic means increasing the speed of the commutation of the transition of the transistor. Sorry. So one possibility to do this is to control it by a femtosecond laser pulse. In order to be able to change, for example, from a conducting to a non-conducting states using femtosecond light, and being able to do this on a femtosecond time scale. Now, I must stress that most of those kind of phase transition are non-thermal in nature. What I mean by this is that if you excite a specific bonding, you can really, I would say, induce a phase which is not present in the let's say in the equilibrium phase of the samples, phase space of the samples. Now, if you concerning the electronic, okay, you may say that the transistor is just like switch on off, and when you are on, you are in a conducting state. So you have the current passing by, and when you are in off states, you have an insulator. So basically, the idea is to be able to act on an ultra-fast fashion in order to change from on to off scales, or from conducting to non-conducting states. Now, the off to on transition, which would mean practically the insulator to metal transition, is something that is easily achieved by laser pulses. We have we can think, for example, the very easy idea we may think of is just if you have a laser and you have a semiconductor and you just excite the electrons across the band gap. Of course, you are increasing the conductivity. You are increasing the conductivity, but you still have a semiconductor, in fact, because you still have the gap. Now, this is, of course, equivalent to a thermal process. What people have shown, what you can also do, is to change, so to reduce the gap by a specific excitation with light, and you can, in principle, even collapse the gap. And this is a purely non-thermal process in which you can control the gap in a fashion which is different with respect to what you may do, for example, by using by simply eating up, for example, your sample. And another thing that's been shown by Andrea Cavalieri was that it was also possible to control the conductivity through controlling a coherent phonon. It means you have a coherent oscillation of the atom. If this phonon is strongly coupled to the electrons in the conduction band, but you may modulate the conductivity at the same frequency of the phonon. This is also, of course, a non-thermal process. So all these things, of course, it's very interesting, but I would say in a certain sense, intuitively are all going in a direction that we can easily understand. You put energy into the sample. So you delocalize more the electron, you give, I would say, more kinetic energy, so you expect to increase the conductivity. What is less intuitive and actually harder to perform is the opposite. Basically going from a metal to an insulator. And this transition only concerned very little number of studies. I personally found only 2 up to now. And it's because of course, it's much harder to go from a metal to an insulator. And this is exactly what I'm showing you today, some recent results we had on this metal to insulator transition that we achieved on a very special sample, because of course the key question you may ask is how could you really reduce the conductivity? One possibility that we've been using is using trap states, localized states in a certain sense similar to Anderson localization. So in order to show you all this, I will first talk about the sample on which we did achieve this conductivity reduction. Then I will show the experimental results with the theoretical calculation and then some conclusion and perspective. So this sample is called in literature LAVS3, is composed of basically 2 slabs, one slab of LAS and another slab of VS2. And the characteristic of this structure is that there is an incommensurability along the direction. It means that the crystal cell along the crystallographic A direction as in a it's incommensurable between this layer and this layer. Now what happens here? That this incommensurability create a modulation in the vanadium distance. So basically, in order to reduce the internal energy, the crystal lattice, just put yourself in like a little more distance, a little less, a little more, a little less. And if you do this, you find that in the place where the vanadium atom gets closer, they form what we call a cluster. And within this cluster has been suggested that there may be some trap states, some localized trap states. They may act in a similar way like Anderson localization. I have to say another interesting thing is that here you have we have that the electrons are basically confined within those layers. So you have a quasi 2D electron gas here within this layer, which is also interesting for some, let's say, for some application. Another thing that is interesting in this material is the current switching they may have. Actually, it has been shown that if you apply a moderate electric field, you may really have a jump of several orders of magnitude in the current. And in the same way of looking at the resistivity, if you apply a little voltage, you may change the resistivity of several orders of magnitude. But let's say the point that's been motivating, let's say, our work was to try to understand if those localized states similar to Anderson states would exist. So let me show you the experimental results. And of course, you will know the answer will be yes, but I will tell you the story the way it has been, I would say, happening, say historical in a historical meaning. So we were using a pump probe technique with femtosecond temperature resolution, just a pump probe scheme, in which we have been using an OPA, and we were using the signal and idler to pump and probe the sample, and looking at the time resolved at the transient reflectivity of the sample. Now, if you look at the pure data, so this is the experiment has been done with a pump of 1 electron volt and a probe of half electron volts. Those numbers are very important. I will come back later on these values. Now, if you look at the reflectivity, the intriguing fact is that if you start from low, here the blue one, okay, you start from low fluence, you have a peak, then it goes down, and then it goes up again. If you increase the fluence, the peak goes higher, but the dip, let's say the plateau, goes lower, until, let's say, a fluence of around half millijoule per centimeter square, from which the transient plateau of the reflectivity goes up again. Here is a version of the vision of the normalized, just to show you how it is the evolution. And this, let's say, these transient states, which is negative for low fluence and positive for high fluence, stand for quite a long time. So we've been measuring up to 100 picoseconds, and it was still there. So it was quite a quite robust transient states. Now, if you look simply at the peak of the reflectivity peak here, you see, as you may expect, simply a linear dependence on the fluence, which is just consistent with the fact that you are a photo-exciting carrier. So it's there is no, I think it's all okay. We all agree with this. But what is more interesting is understanding what happened here if you take, let's say, the value of the plateau. Let's, for example, take the average value here between 2 and 3 picoseconds. Now, if you increase the fluence, first this plateau goes deeper and deeper toward negative value, and then you have change and it start increasing up to positive. So basically you see a non-monotonic behavior as a function of the fluence, which is kind of rare and bizarre, I would say, because you would expect to have, let's say, a linear and monotonic, well, linear probably not, but at least monotonic change as function of the fluence. And there is also a sign change. The most intriguing part here is that in order to try to relate this with the thermal, of course, properties, simply to the heating by the laser, we've been performing equilibrium reflectivity by ellipsometry. Now, if you look at the ellipsometry at equilibrium, you see that by increasing the temperature, the reflectivity always increases, which means that you cannot explain this by the heating up of the crystal. So here we observe what we could call a non-thermal behavior. And what is the question is what it is. Of course, you will see that this is related to the presence of these trap states and to our overall reduction of the conductivity. But in order to understand all this, of course, we have to do some little theoretical calculation. So we did start with DFT calculation. First, I want to draw your attention on the fact that around the Fermi energy, only the T2G level of vanadium are participating basically to the conduction band. Now, if you have a closer look to the partial density of states of the vanadium, you can see that there is this dxy orbital remain unsplit, while the xyz and dxz orbital are splitted. One is below, let's say, one peak below the Fermi energy and the other one above the Fermi energy. In a more quantitative way, means that you're just creating here, as you have a sigma bonding, okay? So you have basically your valence electrons. This orbital correspond to the conduction bonding, to the conduction band, and this sigma star antibonding orbital that would correspond to this localized states within the vanadium cluster. And if you look at the energy scale, this is actually the most interesting part for us, I would say. When you look at the energy scale, you notice that here, if your pump is at 1 electron volt, you can excite either the transition from the bottom here of the conduction band to these trap states, or from the valence band to the conduction band. I forgot to tell you, which is important, that this material is a semi-metal, which means is a metal from the point of view of the band structure, but with a very low density of electron into the conduction band. So now with this pump energy, we can excite both transition from here to here, from this one to this one, and from this one to this one. So we may expect a competition, of course, between those transitions that can be, let's say, easily treated by a rate equation. So just take a simple rate equation, taking care, of course, that part of the energy goes into one transition and the other one into the other transition. Those trapping states, I consider to be, say, very long, very long living states. And here you can see that basically the conduction band first increase because of this transition, but then decrease, of course, because some of the electrons are promoted here. So overall, finally you are emptying the conduction band. All this is from the point of view of the electron dynamics within the band structure. But then you may say, okay, but we know that the laser finally also eat up the sample, and we know from the ellipsometry measurement that the reflectivity also change with temperature. So, and if if you use conservation of energy, you find that, for example, at 2 millijoule per centimeter square, you should increase temperature about 50 degrees. So you must take into account also this. And so we use a simple, say, true temperature model in a simplified way, so without neglecting both electron and phonon diffusion. And we combine all these things. Now, important thing, I told you that we have a probe photon of 0.5 electron volt. 0.5 electron volt cannot induce any transition from the valence to the trap state, to the localized states. It means that the only thing you can probe is what happens within the conduction band. So basically, your change in reflectivity can only be related to the change of electrons of the carrier density into the conduction band, and of course on the temperature of the lattice. Where this beta here, this is very important, it's already known because it's known from the ellipsometry measurement. If you put all this in equation and you compare with experimental results, you can see that the model can capture all the feature of the reflectivity. It's really pretty nice, I would say. And this, in a certain sense, encourages us and show us that really those trap states exist. But then you may argue, okay, well, you say this because you are at this wavelength, you are pumping at this wavelength, but what happens if you change the the wavelength of the pump? And this is actually what we have tried in order to see if our interpretation was overall correct. And we have been trying using slightly less photon energy, so 0.7 electron volt as a pump. Of course, it's a signal and either, so the probe is 0.8, so still below 1 electron volt in order to be able to follow only what happens within the conduction band. But here, below 1 electron volt, we cannot excite from the conduction to the localized states of the vanadium cluster. So basically here, in this configuration, we can only pump from here to here, and we can only probe what's happening here, the same that we were doing before. Now, if you look at what happens in terms of, say, of the changes of the transient reflectivity, you can see that even at those values where we should have the maximum negative plateau, the value of the transient reflectivity is always positive. It's actually always positive, which actually it's fully in agreement with our theoretical interpretation, and in the sense reinforce our interpretation. So this really tells us that those vanadium clusters exist, but more interesting for us is the perspective of the application, because if you are promoting those electrons into the cluster, into the localized trap states within the vanadium, it means that you are reducing the conductivity. So you have a femtoseconds control, a femtosecond reduction of the conductivity. Of course, you may say further study must be done. Of course, I would say that we should make a measurement of the direct conductivity by time-resolved spectroscopy. We should follow in time the clusterization and declusterization dynamic eventually with X-ray diffraction, when we reinforce this cluster by exciting electron into those states. And another way to do it that we are exploring is also to measuring phonon frequency hardening, because basically if you reinforce the atomic bonding, you are expecting a phonon frequency hardening, a hardening of the coherent phonon. Instead, if you are softening it, it's because you are weakening the bonding. In our case, we think we are strengthening the bonding, and so we should have an hardening of the clusterization dynamics. And so let me finish just by acknowledge all the people working here on this project, on the founding agency, and thank you very much for your attention.
Thank you, Boshito, for your very interesting talk. We have time for 2 short questions.
With pleasure.
Thank you very much for your presentation. So you are considering transformation from conducting state to the dielectric state optically, but in reality,
yes.
If you have the current, all these traps, when being filled with electron, will create the Friesen electric field, which will reduce the following pulses. What is the ways to free them before the next cycle of switching is happening?
So you mean how can we free them, right?
Yes, because we have to restore the initial state in the system.
For me, we can restore the initial states by stimulated emission. Basically, you may imagine that if you come with another pulse with exactly the same wavelength, you may promote them to go back to the initial position. It's just like the laser, right? It's just stimulated emission. This is a very long state. These disrupting states, it seems to be very long-living. But what we are trying to do is to put him back again just by using stimulated emission. So we will arrive with the photon just at the same wavelength.
Not thermally, just optically. Yeah. Right.
Just optically, right? Because your point is actually very good and very interesting. Of course, if you have to wait thermally that it comes back, then there is no interest anymore in using ultra fast switching.
Yeah, it will limit the frequency of
course. I completely agree. Yeah. I completely agree, and that's why we are trying optically to switch back.
Mm-hmm. Thanks very much.
You're welcome.
Okay, maybe some short question once more. No? Okay, let's thank the speaker again.
Thank you very much.
And we shift our session to the next talk. The next talk titled Advanced Optical Manipulation with Structured Laser Beams, given by Dr. Porfiryev from Image Processing Systems Institute of Russian Academy of Science, branch of the Crystallography and Photonics, Samara, Russia, please.
Okay. Hello everyone. Yes, my talk is about advanced optical manipulation with structured laser beams. Let's start with definition of structured laser beams. And structured light is a spatially amplitude, phase, and polarization modulated radiation obtained with the help of classical optical elements, diffractive optical elements, metal surfaces, or structured screen. In contrast to the Gaussian beam with the transverse profile of the intensity described that can be described with the Gaussian function. Structured laser beams can have various amplitude, phase, and polarization distribution. For example, we can create laser beams with what? Oh no. We can create laser beams with such amplitude distribution, or this well-known optical vortex beam with helical wavefronts, or laser beams with azimuthal, radial, or hybrid polarization. And all of these features give scientists possibilities to use these structured laser beams in optical communication, laser material processing, and laser manipulation. In this talk, I'm going to show you some examples of the use of structured laser beams for laser trapping of light-absorbing particle in the air. In this case, the laser trapping is based on the photophoresis phenomenon. Photophoresis is defined as the light-induced motion of microscopic particles and occurs when the surface of the illuminated particle is non-uniformly heated. In this case, the gas molecules rebound off the surface of the particle with different velocities, creating a force. And there are two types of photophoresis, positive photophoresis and negative photophoresis. In the case of positive photophoresis, the illuminated particle moves in the direction towards light source, and in the case of negative, in the direction from the light source. And in most cases, for laser trapping of light-absorbing particles in the air, the so-called optical bottle beams are widely used. Optical bottle beams are in fact areas of minimal or zero intensity surrounded by the regions of higher intensity. And it is well known that such diffractive element as a diffractive oxycon can be used for creation of optical segment on the optical axis. But if we change the transmission function of this element and add additional phase jumps, we can change the distribution along this optical segment and add areas of minimal intensity. You can see it from these figures, and these red circles indicate these areas of minimal intensity. These areas are in fact optical bottle beams. And then we can use these optical bottle beams for realization of multiple simultaneous trapping of multiple light-absorbing particles. In this experiment, we use optical setup based on spatial light modulator for realization of phase mask of this diffractive oxycon with phase jumps. And we use agglomerations of carbon nanoparticles for laser trapping. And you can see that in this case we can trap simultaneously three particles. You can see them due to the light scattered by these particles, and this picture in the right corner demonstrate the transverse plane of the trapped particle. You can see the particle and the central ring of the formed optical bottle beam. Of course, optical structured laser beams can be used for generation of various arrays of optical bottle beams. For example, the so-called polygonal beams can be used for generation of multiple three-dimensional arrays of these optical bottle beams, and we can use psi function in this equation in order to control the profile of the area inside the area within which the optical bottle beams are formed. And then we can use such laser beams for realization of laser trapping, and we can trap simultaneously hundreds and thousands of microscopic particles. You can see it from these results, demonstrating the trapping process at different time moments. Of course, we can create more complex structured laser traps with the help of other laser beams. For example, it is well known that superposition of Laguerre-Gaussian beams can be used for generation of various structured laser beams with various unique properties. For example, in the superposition of two Laguerre-Gaussian beams with indices 0,1 and 0,-2, the following rotating clusters of three light spots can be generated. And then we can additionally modify the complex amplitude of this beam in the initial plane. For example, we can shift the beam from the center, and then we can add additional deflecting phase to the phase distribution in the initial plane, and we can change the trajectory of these rotating clusters. And then we can create a superposition of such rotating clusters with curvilinear trajectory and get some more complex laser beams. For example, here you can see a quadric of shifted rotated two Laguerre-Gaussian beam with different individual carriers and propagation dynamic of this beam. We use different colors in order to show the rotation of this beam as a whole and the rotation of its individual components. And then we can use such laser beams for the demonstration of different types of laser manipulation. For example, we can use each of the formed light spots for simultaneous trapping of different particles, like in the left part of the frame. Or we can use this structured laser beam with a curvilinear trajectory in order to realize passive guiding of the trapped particles. For example, in order to show that the trapped particle can go to around some obstacle. Like in these pictures demonstrating the trajectory of trapped particle obtained with the light scattered by this particle at different time moments. Okay, in conclusion, I show you some examples of the use of structured laser beam for laser trapping, photophoresis-based laser trapping, and there is wide possibilities of the use of structured laser beam for realization more complex and more advanced optical manipulation that can be used in various fields. Okay, that's all. Thank you all for your attention.
Okay, thank you. We have a lot of time for the questions. Please.
Very exciting in all ways, I would say. But modeling is quite nice. But what about practical realization? Because collinearity of 3 or even 4 beams is quite non-trivial task in experiment. And also these beams will overlap and interfere and so on. So the aligning will be a nightmare. Can you comment on this?
I think actually it's no problem when we use spatial light modulators, because these results I demonstrated in this slide these results were obtained with commercially available spatial light modulators, and there is no problem.
Okay, some other questions? Okay. If no, let's speaker again. And our session now is closed. And the next session, then the next part of the session begins in 4:30. Okay, thank you for the attendance and for the discussion and for the very good questions. Thank you.
should chair this session. I'm interesting. So as I know, first talk will be presented. Second talk, Shikin, is here. Okay, thank you. Kuchmizhak is from Vladivostok. Probably he'll be in the Zoom or maybe. I'll wait for that. And number 7, Pelegov is here. Thank you very much. So, oh no, not. Last is Khairulina. Thank you. Okay, in this case, I'm announcing the talk number 1, Structured Laser Beams for Polarization Sensitive Laser Material Processing, will be made by Alexei Porfiryev. Same team, same organization. 20 minutes.
Okay, yes, this is my second talk. It's about structured light again, but in this case for laser sensitive, for polarization sensitive laser material processing. I think I can speak this slide. And I just want to tell that in the field of laser material processing, structured laser beam can be used for fabrication of various unique one-dimensional, two-dimensional, and even three-dimensional structure like this. In this talk, in our work, we use two types of polarization-sensitive materials, thin polymer films and nanomultilayer structures based on halcogenate glasses. These materials are promising for a dynamic system of optical conversion, data storage, and recording. And these materials are able to change their structure under the influence of laser radiation, depending not only the amplitude, but also depending the polarization distribution of radiation. So photochemical isomerization of azobenzene molecules between trans and SiC forms results in a decrease of a distance between paracarbonyl atoms from 10 to 6 angstroms. And upon irradiation with linearly polarized laser radiation, azobenzene molecules statistically reorient and accumulate to the direction perpendicular to the polarization plane. In our work, we use thin polymer films with the following transmission spectra, and also we use such nanomultilayer structures based on halcogenate glasses, because we can use these materials for one-step direct laser patterning and fabrication of surface relief without any etching. Okay, let's start with a simple thing. Here you can see result of laser process patterning of thin polymer films with the help of linearly polarized Gaussian beam. Here you can see intensity distribution of initial laser Gaussian beam with different linear polarization orientation, then total intensity of focused laser beam, and all three components. And also we can use the inverted longitudinal component of the focused laser beam. And here at the top right angle, you can see profiles of the fabricated microstructures, fabricated in thin polymer films. And you can see that the profiles of these structures are very well coincide with the distribution of the inverted longitudinal component of focused laser beam. In this case, the temporarily molten polymer moved along the polarization direction from regions of higher intensity to regions of lower intensity. And in this case, we can say that this thin polymer film, that these results shows high sensitivity of these thin polymer films to longitudinal component of laser radiation, illuminated laser radiation. Okay, but what happens when we use non-uniform polarized laser beams? For example, cylindrical vector beams with such Jones vector. And here you can see examples of cylindrical vector beams of different orders. And it is well known that the profile of these laser beams are in fact rings. But the profiles of the fabricated structures shown in this slide are different. In fact, the profiles of the fabricated microstructures are sets of zips and protrusions located around the circumference. And it is, again, in this case, these profiles very well coincide with the inverted longitudinal component of illumination laser beam. And we can use these profiles in order to determine the polarization order of illuminated laser beam. And our last result with these non-uniformly polarized laser beams is it demonstrates the use of hybridly polarized cylindrical vector beams. In this case, you can see that the total intensity distribution and the longitudinal intensity distribution are very complex, and it's not rings. But again, these thin other polymer films can be used for visualization, perfect visualization of this longitudinal component of the light. So we can use thin other polymer films as detectors of this longitudinal component of light. But it results for single laser beams. It's obvious that we can split this single laser structured laser beam into a set of identical laser beams, for example, with the help of diffractive grating. Then we can use 4F optical system and realize additional spatial polarization filtering. And we can change the polarization of each of the formed light spots. In this case, we can use various polarizing elements, for example, various Q plates of first or second order, in order to realize this polarizing filtering. In our work, we use optical setup based on spatial light modulator in order to realize phase mask that can be used for splitting of initial Gaussian beam into a set of 25 identical light spots, and then we can use Q plates, for example, as I said, in order to perform this polarization filtering. And then we can use these laser fields, non-uniformly polarized in this case, in order to process thin other polymer films, and we can get the following results. Here you can see results for 3 cases when we use half-wave plates as the polarizing elements, and when we use a Q plate of first order and Q plate of second order for polarization filtering. And it is obvious from these pictures that the profiles of the fabricated reliefs are in fact sets of protrusions, micro protrusions with different orientation. And orientation of these protrusions very well coincide with the direction of polarization vector at this point. So we can use thin the polymer fields also in order to visualize local inhomogeneities of polarization plane, of polarization distribution. And it is well known that when we use cylindrical vector beams and such hybridly polarized cylindrical vector beams for laser processing of thin metal films with pulse radiation, we can create laser-induced periodic surface structures. These lips are formed at the nano layer, but the result demonstrated at the previous slides were obtained at the micro level. Of course, it is possible to create sub-wavelength laser-induced periodic surface structures in photosensitive materials too, and I show you some examples of the use of structured laser beam for creation of surface relief grating with submicron periods in the next slide. It is well known that interferometric approach it is well known that interferometric approach widely used for fabrication of surface relief grating. In this case, the interference of two laser beams results in the generation of periodically changed intensity distribution. But it should be noted that in this case, not only the intensity distribution, but also the polarization distribution of the formed light field is periodically changed. You can see it from this result demonstrating the interference of two circularly polarized laser beams. It is very interesting that a Gaussian beam with such polarization distribution can be formed with the help of one special element, optical element, the so-called depolarizer. And depolarizers are in fact patterned micro-retarder arrays and can be described as a set of half-wave plates. It is possible to imprint a pattern of different half-wave plates with different fast axis orientation inside liquid crystal polymer materials, and we can create depolarizers in this case. Here you can see example of one commercially available depolarizer that can be used for the transformation of initial linearly polarized Gaussian beam into a Gaussian beam with such polarization modulated distribution. And then we can use this beam with such polarization modulation for laser processing of Hawking glasses or thin as polymer films in order to create surface relief gratings. In this experiment, we use a spatial light modulator for laser beam steering. We can control output laser power in order to control the relief height. Also, we can control location of this depolarizer in a setup in order to change the period of the fabricated surface relief gratings. And in this case, the minimal period was approximately 4 micrometers. And finally, we can rotate the depolarizer during laser beam scanning in order to change the orientation of grooves of the formed surface relief gratings. And here you can see examples of the fabricated space variant surface relief grating with discretely and continuously changed groove orientation. And these pictures are very similar to the pictures of laser-induced periodic surface structures shown in this slide when we use cylindrical vector beams for laser processing. But as I said, in this case, the minimal period was approximately 4 micrometers. But we can achieve sub-micron periods when we use two stacked depolarizers. These depolarizers have the same profiles, but when we rotate one of these depolarizers relative to another, we can change the period of polarization modulation. You can see it from this picture demonstrating cross-polarized images of these two stacked depolarizers. And in this case, we can achieve sub-micron periods. And then we use these laser light fields for laser processing of Hawking unit glasses. And the minimal period of the fabricated surface relief grating in this case was approximately 950 nanometers. But when we it is possible to decrease this value if we can, or if we will use micro objective is higher in numerical aperture, or if we will use more stacked depolarizers. Yes, and in fact that's all. I hope this demonstrated results show you wider possibilities that can be obtained when we use structured laser beam for laser processing of polarization sensitive materials. And that's all. Thank you all for your attention.
Thank you very much for your nice talk. Please, questions? Yes, please.
The gratings, relief gratings in other polymer films, how stable are these gratings? What happens in a month and so on?
In fact, we didn't check it, but this thin as a polymer films was provided by our colleagues from Moldova Republic, and we got this these samples 2 years ago, and there is no difference between structures now and then.
Okay, more questions. I have 2 questions. Let me know, please, which laser do you use and how you produce the structured beams?
We use green laser, 532.
Okay, which power? Sorry.
Which power? It's in fact the power in the plane of the sample was approximately units of microwatts. Yes.
It's continuous wave, so
yes, it's a CV laser, and in order to generate this structured laser beam, we use spatial light modulator.
Now, wait, how do you produce structured beams? Special modulator?
Yes, yes.
Homemade?
Nope. Hollow eye. Pluto
Hollow eye.
with.
Okay, thank you. Last question, please.
The beam laser you have used has the wavelengths close to the absorption band of other polymers.
Yes.
Have you observed some degradation, destruction of the other polymer?
Degradation? Nope. Only laser patterning. Because I think the laser power that we use was low enough in order to achieve any degradation.
Okay. Thanks again to speaker. I have received the information, you can go. I have received the information the Kuchmijak will be in the virtually in the Zoom, so it also will take place. Now we can go to the next talk, femtosecond pulse inscription of fiber break gratings with phase shift by motion velocity modulation. Shocking.
Hello, my name is Artyom. I'm from Kotelnikov Institute of Radio Engineering and Electronics. And today I will talk about inscription of fiber break gratings with a phase shift by femtosecond pulses and velocity modulation. So in the beginning I will shortly cover what is fiber break gratings and what the applications, and I will also talk about what is phase shift, and then I will move to hello, and next I will move to fabrication methods, what our novelty and what advantages we suggest, and what results we get with our methods. Fiber gratings is a periodical modulation of refractive index, and period of such modulation defines the position of a reflection spectrum, and length and strength of modulation defines the amplitude of spectrum. And if we have displacement between two consecutive points of modulation, then we will get a phase shift. Combination of flexibility of break gratings and light confinement in fiber has found application for fiber lasers, and today phase shifted fiber break gratings are very attractive for fabrication of single frequency lasers, which can be used in sensorics or communications. If we talk about how we can fabricate gratings, there are two major ways, either by using photosensitivity or using multi-photon absorption. First one is traditional and well-established technology, which mostly use UV exposure, and it's pretty simple. But for fabrication in active fibers, especially in erbium-doped silica fibers, we need a hydrogen loading. And it was shown that for this type of fibers, hydrogen loading can bring disadvantages in laser properties. And novel technology of femtosecond pulses exposure has advantage of using it in any kind of fiber, and it's more flexible. It doesn't require phase mask, and but it has this advantage that it requires high precision equipment. And, nowadays, there are motion stage which can allow this precision, and therefore it's possible to use femtosecond pulses. On the left, a typical scheme of such equipment is presented. Fiber usually is fixed on a horizontal part of stage with nanometer precision motion, and laser is focused through lens into the core of the fiber. And usually we use a 100 magnification lens. Typically, light is pulsed with fixed frequency, and fiber moves with constant velocity. And to have a displacement between two consecutive areas of modulation, one needs to somehow modify this equipment. One way was to introduce additional acousto-optic modulation, and the other was to introduce additional piezo stage. Both methods gave good results in single pass inscription, but for multi-pass inscription they can struggle, because usually time between two areas of modulation is around 1 milliseconds, and inter-chip communication, when there are several equipments and there are cables and interfaces, there can be struggles. And our motion stage allows to load program exactly into the stage and to have a modified velocity during the motion. So we use constant velocity till our point of interest, then we raise the velocity, and then we break the velocity again. And it happens almost instantaneously, and results show that it's possible to fabricate displacement short and precise and repeatable manner. So the picture on the right is a 5 millimeter long Bragg grating inscribed in typical single mode fiber, and the dip in the middle of the fiber is exactly what is called pi shift. It's attributed to this displacement. Usually fiber Bragg gratings has a single peak. And if we inscribe a longer fiber Bragg gratings, like 30 millimeters, we didn't see this dip in usual spectral analyzer. We needed to use something more sensitive. And that's why we use a switchable laser with 5 picometer sensitivity resolution. And we were able to see not only the dip in the between, but also we saw that this dip is doubled. And this is attributed to asymmetry of interaction between laser pulse and fiber core. And as the goal of our experiments was to fabricate fiber laser, we inscribed the 30 millimeter long gratings in erbium doped fiber, and we were able to obtain laser generation. It wasn't very strong, it was only 20 microwatt height, but it was a generation, and what's more important, it was pretty narrow. We use a self-heterodyne method to measure line width of this pulse, and because our delay in line was less than coherence time, we estimate our line width about 1.5 kilohertz, which is a pretty good result. And therefore, we show that we know that fiber gratings is attractive for fiber lasers, and is desirable to produce gratings in controllable manner, and only a few groups in the world can do this in a multipass method, and our patented technology for multipass gave this possibility. And here I presented that with multipass we can also fabricate pi shifts, and we demonstrated that our pi shifts can be used for fabricating erbium doped fiber lasers. Thank you for your attention.
Thank you. What is the resolution of your method, and what is the period of the grating you have produced?
So the grating is optimized for 1.5 microns. It's pretty flexible technology, so we can fabricate it 1.3, 1.5, and we can control it with a precision somewhere around 0.1 nanometer. And it's more defined by grating width. So the longer the grating, the narrower the width also. But here we're also interested in pi shift and generation.
So you have really fabricated the single frequency fiber laser. How the frequency of this laser depends upon the temperature of the fiber?
Yeah, probably we didn't measure it, especially like temperature-induced changes. But in general, it has slight negative. The gratings are pretty sensitive to temperature, so one needs to stabilize it with some elements, cooling elements.
Some more questions? I have one question also. What benefits you have from the modulation of motion velocity?
So the major benefit is that we have simple and stable possibility to place our pi shift. So we want to have it. We want to have two areas of modulation relatively fixed. So the distance between them will be the same from pass to pass. So we use multi-pass technology when we write it pulse by pulse, and then we do it again.
Okay. If no question, let's go further to the program. Now we should have the talk from Vladivostok by Zoom. Who is rule the Zoom? Sasha, привет. Как ты?
Good afternoon. Good evening already in Vladivostok. Almost night time. Okay, so I will start screen sharing. Okay, do you see my slide?
Okay. 15 minutes here. Only remind him. So, Sasha, you can begin, but take into account you have 15 minutes, please.
Yes, yeah, I remember. Okay, so many thanks for for this introduction. Today I will be speaking about the structural color marking and security labeling by ablation-free femtosecond laser processing. And actually, to start with, I want to remind you that we have a lot of goods, a lot of important things that requires protection from forgery. And actually, probably the most striking example where the forgery can cause direct harmful impact into the patient health is forgery of medical drugs. And there are a lot of different common technologies for protection of valuable things like watermarks, like holograms and so on. But once the technology matures, more and more facilities can actually replicate the same technology and use for forgery of valuable things. So there is a huge need for development of novel and advanced methods for security labeling, and the modern trends includes the miniaturization of the labels, at least to protect them from the naked eye. Also, there is a huge adaptation of different encryption schemes to make, for example, some labels visible only under very specific conditions like specific excitation or surroundings. And also there is a good approach involving physical unclonability when you introduce some randomness into the fabrication process. So each time you produce labels that are rather random, so you cannot copy this label even with the same fabrication technology is used. Important thing is the optical labels, meaning the labels that is used that are used according of the optical signals like local reflection or photoluminescence, because these labels can be perceived or detected or identified just by naked eye or by, for example, a CCD camera on your smartphone device. And there are often structural color effect is often used for optical label fabrication. And just to illustrate the structural color effect, I put here the photograph of maybe the most common naturally inspired example of the structural color effect. It's the wings of the morpho butterfly that have this nice blue color appearance, not because of any chemical pigments, but because these wings have a non-structured surface that act as a optical filter that resonantly reflect on the blue part of the visible spectral range, appearing as this blue color. And of course, as there are no chemistry inside, so these structural colors can be considered as non-fading, as rather stable against the temperature or UV exposure. And once the nanofabrication technology evolves, there are huge opportunity to design artificial and complicated optical resonators that can act as a structural color structures, allowing to control the local reflectivity at sub-microscale level, so it's a level of isolated nanostructure. And this technology, of course, is very promising for high-resolution color display and, of course, for designing of different security labels in the form of some kind of micro-scale images. And in this slide, I put the structural color image printed at a very high resolution. It's about 100,000 dots per inch, so you cannot resolve with the optical microscope, with the best optical resolution, you cannot resolve the isolated pixels in this image because they're printed at sub-wavelength resolution. But generally, these mentioned nanostructures are typically fabricated by rather expensive and hardly upscalable lithography-based fabrication technologies. So there are huge demand of more inexpensive, more cheap and high-performing and practical-ready solutions. And I want to highlight the direct laser nanofabrication that we all know that is flexible and more cheap comparing to the ion beam lithography. But there is an issue with the diffraction, of course, so we are limited by diffraction, our focusing capabilities and our resolution. So this is rather questionable whether the direct laser nanofabrication can be used to create the security labels or structural or nanostructures possessing structural color effect at very high resolution. And I want to present our technology on fabrication of structural colors, and this technology is based on unique interaction of tightly focused femtosecond laser pulse with the thin noble metal films placed on the substrate. And this actually, this interaction includes the thermalization of the electron at femtosecond time scale, launch of the acoustic wave at the same scale, melting that proceeds already at the picosecond time scale when we just have the end of our, just after the end of our femtosecond laser pulse, relaxation of the molten part of the metal film also at the picosecond time scale. And finally, retardification is the nanoscale that creates the hollow parabolic shaped nanostructures, which size increases with the applied pulse energy. And the structure is hollow, as you can see here, by this set of cross-section, focus ion beam cross-section images. And probably the most important thing here, that fabrication process is ablation-free, meaning that we have no ejection of debris or eruption of the metal film during this fabrication. So this process is rather stable, allowing to create the arrangement of these nanoscale structures. These nanostructures, as we previously shown, possess the tunable plasmonic resonances with the position of the resonant that can be tuned by tuning the morphology of these isolated nanobumps and their arrangement. So fabrication process is rather controllable and flexible, so we can design advanced plasmonic platform for different applications, for nonlinear photonics, for plasmonic sensing, also for control of the emission of the quantum dots. We attached to this device as we recently work done in collaboration with Professor Andrei. Also, I want to highlight that nanostructure possesses the plasmonic properties, so it can be considered as electrically driven source of visible and near-infrared radiation. However, today we're speaking about the structural colors, and the one important thing is when we just irradiate this nanostructure by white light from the side, as shown here, and we collect only the scattering signal, these structures, when we use the S-polarized white light excitation, the structure demonstrates very nice and tunable scattering mediated by surface plasmons. And actually, for S-polarized excitation, we have nice tunability of the scattering color because we excite only axial types of plasmonic mode, not just a mixture of different plasmonic modes. And for S-polarized excitation, we have very nice tunability of the scattering maximum that define the scattering color. That is actually scales, linear scales with just a circumference or arc length of this nanobump structure. The structural colors generally are almost weakly dependent on the collection angle of our objective used to visualize these nanostructures. That is a good story for application. So with this technology, we can fabricate nanostructures at a resolution of 25,000 dots per inch. So we can create some colorful images that can be visualized in the dark field or scattering regime. However, everybody who are familiar with this technology can easily replicate your labels. So because everything is under control, you control the color just by controlling the parameters of your laser fabrication. But we found that if we just switch to a little bit different structure that can be produced exactly on the same system just by increasing slightly the applied pulse energy, so the structures looks like nanojets with nanoparticle at top, we found that even fabricated with the fixed laser parameters, each fabrication run provide us with a very random distribution of the scattering color, because the scattering color in this case is very sensitive to even very small deviation of the size of these nanostructures, namely the nanojets with the nanoparticle. And with this, actually, we can fabricate physically unclonable labels. And for this label, of course, we need some algorithm that allows authentication and validation of the label. So, for example, the manufacturer can fabricate the label in the form of, for example, QR code or any other shape. And so he make the image, optical image of this label. Then the software make the digitization, decomposition into the red, green, and blue color channels. And then the software proceeds through the discretization to each of the channel proceeds through discretization to a several intensity level that can be chosen on demand. And this actually digitized version of the label can be stored in the manufacturer database. And if the end user just want to check whether his label is a real one or duplicated, he or she made the same procedure of just optical optical processing of the image, and then the software compares similarity between the images made by the end user with those stored in the database. And actually, if we just take into account that, for example, this label, the size of this label is only 64 by 64 pixels. So the encoding capacity, which have the meaning of number of tries that requires to just intentionally or occasionally replicate the same label, which will be accounted by the software as the same label. So the encoding capacity is 10 in order of 895. So it's a rather huge number. So this label, even this small label, can be fabricated in a very fast way. It's very hard to duplicate. Okay, so what I show is a result on the structural colors that can be visible in the scattering regime. But if you will just fabricate the nanobump structure above the metal film and have a look what's happening in the reflection, we just see the reduce of the reflectivity because of the broadband absorption of the plasmonic structures on the interface. But if we will design some more sophisticated system like a gold film placed above the dielectric spacer and placed above the bulk reflecting mirror, and if we'll just tune the thickness of the dielectric spacer to make it support a Fabry-Perot mode, so we have this very nice and narrow modulation of the reflection spectrum in the visible spectrum range. And if we will then imprint the nanobump structure on above the gold metal layer, we will see the structural color appears on the surface. And I will show you the video how the process looks like in reality. So the laser beam scans the surface. It's a three-layer system like shown here. And the structure formed in the surface when the laser beam scans the surface of this top gold layer. And you can see immediately the appearance of the structural color. It's a blue color. And actually, we check that the structural colors doesn't change much when we change the collection angle or numerical aperture of our lens used to collect the reflection signal. So this means that our structural colors comes not from any grating type arrangement of the nanostructure, but from the absorption of our local nanostructure. So we can play with the different parameters like a pulse energy to control the geometry of nanostructures and their arrangement on the surface to design different color pixels where we can control the colors at the micro scale level. And the general concept why the tunability is happened is it's a plasmonic absorption of our induced by imprinted nanostructures on the surface. And just to illustrate the technology application, I put here the optical image of the structural color image printed using 15 different color tones, namely 15 different fabrication regimes. As you can see here, we can also produce the white color and even black color on the surface. So the white color corresponds to the case when we remove the dielectric spacer, and the black color when we already start to pattern the bulk reflecting mirror. And probably the last thought I want to disclose, it's a fabrication resolution, and it's typically so the resolution is actually the distance between the minimal distance between the two adjacent nanostructures we can achieve. And here we of course limited by fundamental diffraction limit, and for our green laser wavelengths we have we can expect the resolution of I'm almost finished. About 600 nanometers. But when we work on ablation-free regime, we found that we can work with the overlap printing the nanostructures much closer to each other. And with this, we can design the pixels where actually their colors cannot be resolved even with the best optical microscope because of the sub-wavelength arrangement of these nanostructures. That's allow you to create the really nice and really high resolution optical images that can be used for security labeling, as you can see here. So, okay, I proceed to the summary, and today I try to convince you that direct laser fabrication provides you remarkable opportunities for fabrication of different security labels. And also I want to thank our guys, our collaborators, Russian Science Foundation for support, and all of you for your kind attention. Thank you very much.
Thank you for your talk. Unfortunately, time is over. One question, please. If nobody has no questions, I'm sorry. I have one question. Am I right that to produce your labels, you need to put on the surface, some surface, thin film? So
Yes,
you
sure.
cannot do it on any surface, only on thin film. Yeah?
Yes, and more importantly, we can do it with the noble metal films.
Yeah.
Not
Films.
not any
Not bulk.
any, yes, not bulk.
Yeah. Last question, please. Last question.
My question is about stability of your structures, how they defend from oxidization and how they evolve with time.
Yes, they are very nicely protected from oxidization because they were made basically from gold. So they are rather stable. So you just need to protect them from this debris from the atmosphere. And you can do it by, for example, coating them with, for example, thin layer of something like a silicon dioxide that will be super hydrophilic. So you can wash away some debris.
Okay, thanks again to our doctor. So now the next talk, Pelegov, okay. Laser-induced processes in lithium battery materials studied by micro-Raman spectroscopy.
Let me start maybe. You see, my name is Dmitry Pelegov, I would like to speak about lithium battery materials and Raman spectroscopy because this combination can provide us a lot of interesting results in field of laser-matter interaction. No, this is not my presentation. Maybe it's in other folder because I bring it during the first coffee break. Pelegov. In the previous folder, try to find it. Yes, this one. So you see, to convey the practical importance of this problem of studying laser-matter interaction for lithium battery materials is rather obvious because today this material produced in huge amount, and you see it's used in electric vehicles, for smart grids, for renewable stabilization and so on, and the amount of this produced material will only increase. And Raman spectroscopy was shown to be a rather effective tool to characterize this material, and the only problem that Raman spectroscopy is an elastic light scattering, and we have to keep in mind that this laser-matter interaction can induce defect, and we have to understand how to distinguish induced defect and inherent ones. From the point of view, you see, yeah. And from the point of view wider, broader interest, there is, as for me, interest from fundamental point of view, because you see, frankly speaking, lithium battery materials are the terrible materials for studying by physical tools. They have a lot of problems, but let me name two principal ones. First one, we work in the case of lithium battery material with micron and submicron particles of irregular shape, because they mostly synthesized by solid-state method. And shape and size doesn't matter much in case of laser-matter interaction, and especially when we speak that the size of the object is about the same size as the wavelength of the problem irradiation. Second problem is that usually these materials are rather low conductive, and in this case the conductivity and optical properties can drastically change from particles to particles. So every particle is different. It's no kind of average value to understand its optical or electrical properties. And does it problem? For me, it's not a problem, but an advantage. Why? Because you see, when we study laser-matter interaction, we have to find some peculiarities. And how to find peculiarities? In case of bulk materials are usually more perfect, and it's harder to find peculiarities. Second point, that in case of bulk materials, you see, this small irradiated point usually is stabilized by the larger bulk. In case of nanomaterials, situation is different. We have a lot of peculiarities, but it's rather hard to find it because it's hard to visualize nanoparticles and hard to measure response. In case of microparticles, we can, from one hand, steal a lot of anomalies, defects, peculiarities, but from the other hand, they are large enough to use multiple tools, including very convenient Raman spectroscopy, because Raman spectroscopy combines laser action and characterization in one experimental setup. So we can perform in situ measurement. Let's proceed with results. It's rather convenient that there are only 3 main classes of electrode materials commercially used with layered structure, spinel and olivine. Let's start with olivine. Lithium iron phosphate, this material is widely used in Chinese electric car and even in Tesla, made in China. Usually, in fact, the LFP is a transparent material and rather stable. When we studied 75 particles, only 6 of them degrade. But how they degrade? Here you can see with the width of the image is about 5 microns, so it's about several microns in diameter. 4 of particles melted down. And we suppose that this melting was non-thermal, with not due increase in the temperature. So this process is rather common for femtosecond laser, but for such conventional laser using Raman spectroscopy, it was not observed earlier. Let's skip this material and proceed with another material, with spinel structure. You see, here I will show you results of doped lithium titanate. In fact, the pristine lithium titanate is very stable material. It's very stable from both electrochemical point of view. It can be charged and discharged numerous times, and from physical point as well. But its problem is that this material has a very low electrical conductivity. And if you try to increase this conductivity by doping, as for this material, you increase not only electrical conductivity, but the probability of the laser-induced processes, and it's great because it can provide us a lot of interesting results. In this case, we have double action. First, we take 7 particles and irradiate it there by maximum possible laser during Raman spectrum measurement. They were stable, nothing happens. But when we return to the same particles about 2 or 3 weeks later, we have found that 3 of them degraded without any change of shape. 2 more particles became stable, and you see during the following Raman spectrum measurement with maximum spectra remains the same lithium titanate, but 2 more were initially lithium titanate but degraded just during the Raman spectrum measurement. And these 2 particles are particles surrounded by some nano-object. And it was rather interesting because these nanoparticles are kind of ablation products, but there is no any other evidence of ablation, no fragmentation, no holes, no any damage of these particles with highly complicated shape. We suppose that this indicates us a very important thing, that when you switch laser off, the experiments is not ended, because we have fast and slow degradation process. During the first measurement, we accelerate some physical and chemical degradation process. They continue during the following time, and when we return to the same particles, we can see that something happens. And in this case, we suppose that it was a kind of degradation in the point contact between particles and copper substrate, and this degradation product became the target of laser ablation, and upper part became not damaged, but bottom part was ablated. So another interesting result confirming that experiments of laser-matter interaction don't stop after switching laser off is results obtained for lithium cobalt oxide. Here you can see that we have measured 21 particles 6 of them degraded, and here you can see the optical images and spectra for 2 of them. During the increasing of laser power with these 2 particles degraded, and when we examined them after the switching laser off, they was just a little bit damaged, nothing, no kind of, you see, ablation products around. But when we turned 8 days later, we have found very nice, patterns around these particles. From in the upper row, you can see the images obtained with the focus on the particle. The bottom one with the focus on the substrate. So it's just the same pattern, but with different focus in the direction. It's very complicated to understand what we have, what's the material. We can see only enhancements of the response from the silicon substrate, but we don't have tools able to understand the composition of these small materials. And finally, one more result with, again, the material related with LCO, with layer structure, but this material is more common today in electric cars. Some of cobalt substituted by nickel and manganese. Situation a little bit different. Again, after a series of measurement, particles degraded. As you can see on the right 3 rows, the decomposition, ablation patterns, decomposition patterns are not so nice. It's not so pronounced. But during the measurements, this particle jumped away from the laser beam, and you can clearly see that as the upper right image jumped the left particles, and in the last is the right bottom jumped the right one. So maybe jumped, maybe rolled out, but you see, we have examined 4 different materials. And every materials behave in different manner. And you see, this shows that there is a lot of interesting laser-matter interaction peculiarities in the field of, for example, lithium battery materials. And a few conclusions. First one that I hope we demonstrated that the Raman spectroscopy is unique and perfect tool to characterize laser-matter interactions. Second one, very important, all this pattern, all this result will be lost if we use measurement in powder. Measurement of single particles is much more informative. It can combine Raman spectroscopy, electron microscopy, and so on. And 2 more conclusions. Also, it was rather interesting to find that in various particles, in various materials, we suppose non-thermal effects, even though they are supposed to be observed for femtosecond classes, but anyway. And the last one that it's important to keep in mind that there are not only fast degradation processes, but also slow one. That's all. Thank you for your attention.
Thank you very much. I'm sorry. Let me to ask the first question.
Yeah.
But when we go back to lithium batteries, what is your recommendation for lithium batteries? I didn't understand.
You see, for lithium battery, if we talk about lithium battery, it's using Raman spectroscopy for characterization defect is not problematic if you understand the degradation process, so you can distinguish the inherent defects and degradation products. But this kind of material is interesting to study the variation of degradation process. Also, another point, in fact, why it can be interesting for electrochemical society, because this community is optical, I didn't mention it. But in fact, it's highly complicated to measure degradation process in batteries. They're very important, but usual degradation takes years. And Raman spectroscopy is a kind, for me, a way to accelerate and see what can happen, and use this knowledge to understand the chemical degradation during the cycling or during the increasing temperature and so on.
I will ask in other manner. When you did not irradiate the lithium batteries with laser, what happens with them?
Oh, it's too complicated.
That's a joke. Okay, please.
My question is quite similar. What for do you want to use a laser? To process a battery or to...
To study, to measure Raman spectra. Diagnostic, because you see, what is the problem? Today we produce a lot of batteries. At one day we have to cut cost, and batteries will be different. And it will be great to find these defects. Yeah, for defects, for defect characterization.
The lithium battery is a tool to study the process, not the aim, as a tool.
Both. Okay. It's both target and...
Not object. Not object. Okay, other questions?
To the left.
Oh, yes, please.
And my question will be almost the same. Thank you for your talk. Did you study what will happen if you don't irradiate your particles?
Yes, of course, because we have a lot of particles. You see, when we sediment particles, we have a huge amount of particles, and when we can return back to this particle. And for example, when we see such kind of patterns, we always come to other particles and see that, for example, these concentrated rings were observed only around degraded particles. All the other particles, it was more than 10, had no such variety. Also, we can return to all the others and compare them. Single particles approach can combine various, you see, action and combine how it results in a change of material.
So this degradation is really
yes.
I suggest
because we know every particle, we know in phase, because we have a spatial marks, and we know that we're working just with the same particles, and we can see the same particle by Raman, by scanning electron microscopy, by ADX, for example, and other local tools, and can return again and again to the same very particles, because it's a lot of interesting slow processes for these particles.
I suggest to call this talk as a clear science, not as applied science. Thank you very much for the talk. Now we go to the last talk of our session. The Irina from St. Petersburg University, laser assisted synthesis of electrode materials from Institute of Laser Chemistry, yes?
Yeah. Mm-hmm. Good afternoon, everyone. Thank you for introduction. I'm deeply sorry for some technical difficulties. As I can see, there are some problems with the phones. I hope it's not going to be throughout all presentations, so I'm a bit sorry. So today I would like to discuss with you laser-assisted synthesis of electrode materials and to discuss laser-matter interaction with more chemical point of view to produce some functional materials. Especially electrode materials for electrochemical sensing. Electrochemical sensors can be divided into huge groups. In the first one, we use the enzymes or fermions as a biological agent for recognition of analytes. And the second one works without this biological element. And the second one offers to us a great advantage of high sensitivity, because the reaction with analytes take place on the surface of electrode, so there is no any obstacle for electrode transfer process. And this kind of materials also way more stable in terms of long-term storage, because the ferments, it's biological molecules, they kind of fragile, they are afraid of temperature variation, pH, humidity, and so on. So a lot of efforts currently are putting to develop various kind of non-enzymatic sensors. And electrochemical sensors can be presented in very different ways. For example, like small test strips or laboratory-sized beaker. But anyways, there are three main functional elements, like three electrodes. It's a reference one, counter one, and working. And working, it's the heart of this device. It defines the whole property system, like sensitivity, selectivity, linear concentration range. And today I would like to discuss some laser-assisted techniques to produce working electrodes. And electrochemical sensors has a very wide range of application, from healthcare to food industry, and therefore they have quite wide range of requirements depending on the application, but nevertheless every single electrochemical sensor is supposed to have electrocatalytical activity to the target analyte, height adhesion to substrate, and it's very desirable to have such a technique that very flexible for in electrode production to deliver electrodes for different application. And in these terms, laser processing offers unique combination of conditions to produce specially selective, to deposit specially selective electrode materials on the substrates. And here I'd like to introduce you 4 different techniques we used in our lab or with our collaborators. This technique mainly focuses on the metallic structure on the electric surface. Of course, we can use carbon-based materials for sensing properties, but it's a bit out of scope of this talk. So the first method, it's laser-induced metal deposition, is a technique where we just use very simple, very basic optical setup, continuous wave laser and focusing lens, and we focus on the surface substrates in the solution. And this solution contains precursor of the metal. It can be salt or complex of the metal, and laser radiation via heating initiate metal reduction to form the metal structure on the surface of dielectric. So this way can be produced very different type of metals, even composite, polymetallic composites. But the main disadvantages of this process is low speed. So we developed the modification of this approach. We switched from the water-based of organic-based solvents with a common used solvent like water or acetonitrile to so-called deep eutectic solvents. It's more viscous solvents, and we can switch from the liquid cuvette to the film prepared by spin coating. About this technology, it's going to be 2 talks tomorrow by my colleague and Dmitry Shestakov and Alexandra Levshakova. If you're interested in the application of deep eutectic solvents, I'd like to invite you to their talks. It's a very blooming field now, and we're applying it for laser synthesis of metallic structure. The third approach is selective laser sintering. It's also technique allows us to work without the liquid precursor. It's only difference from the previous one is that we use the nanoparticles as a precursor. It can be metallic nanoparticles or metallic or oxide nanoparticles, which get reduced under the action of laser radiation. But nevertheless, we kind of write down by the laser, metal trucks washed away the untreated parts and result information of metallic structure on the substrate. And the second approach I'd like to introduce to you, it's selective surface activation induced by laser. Here we radiate by laser not the precursor film or precursor solution, but the substrates itself on the air to form sponge-like surface. And then by this laser-induced modification, it allows us to selectively plate copper on the surface of the electric, polymers, glass, and so on. And I'd like to stop a bit more detail on the last approach, because this one is very vividly highlighted the benefits we can get from the combining of laser-induced processes and chemical synthesis. And here you can see the photograph and some images of the modified substrates under the action of laser radiation and the substrates after copper plating. And to get the sensors with improved sensing properties, we modified these copper layers with gold nanoparticles and copper oxide nanowires. So here is a brief introduction to the technique we used. It's electrochemical oxidation of copper, previously synthesized copper layer, and galvanic replacement of copper on gold. So the previously synthesized copper layer allows us to localize the chemical modification because we use this copper layer as sacrifice structure for further modification. And so using only one electrode layer, we can produce a different kind of electrodes in the end by chemical modification. So it's a very promising way to get varieties of the materials based on one laser technique. And so here routine characterization of our electrode. After synthesis, we have small lines on the conductive lines of the dielectric substrates produced by any methods discussed above, and then we get characterize this material by cyclic voltammetry, then by chronoamperometry to measure analytical signal itself. So, and then from this data we collect a calibration curve, and finally we check the selectivity of proposed sensors. In this case, it's example on the glucose detection, so we used uric acid, ascorbic acid, and paracetamol as a common interfering agent. And as you can see in the optimized analysis condition, the sensors shows us quite good selectivity. So here, a small digest of the material we investigated and the parameters of these sensors. So now we can determine glucose, hydrogen peroxide, dopamine, and any other substance they did not include in this table. And I would like to thank our team for this work, and thank you for your attention.
Thank you very much. Please, questions. Yes, please.
Here we focused only on the metal electrodes. One may produce the sensors based on conductive polymers like polyaniline and so on, but usually as for metal or oxide system, it's they are both more stable. So when you use inorganic material, it's way more robust than any organic polymers or enzymes.
I have a question. What about reliability of such electrodes? How long lifetime of them?
It was not presented here. We usually check the analytical signal during the 1 month, like each day, and usually it's degrade about 10% of initial signal, and it's quite okay if you check it with another with literature, but sometimes for example, for review, we need to check it again after a long time, and the longest period of time we checked after the first time, it was half of the year, and it was like the same 90%.
Thank you. More questions? Yes, please.
You are asking about this?
Yeah. About this.
Actually, we didn't check it, so it was not the point of this work. Here we, after the covering of the copper, it's mostly doesn't matter because we growing the copper layer above this modified surface, so the sensor doesn't sense this roughness of the initial surface, and it doesn't affect on the adhesion in the condition of the test. So that's why we didn't pay attention to this question.
And what was the thickness of the metal?
It's about 10 microns.
Okay, thank you.
Okay, if no questions, thanks again to speaker. And session is over, and let me thank all the speakers, and see you tomorrow.